Hello, everybody. Thank you for joining us today, and welcome to our webinar with Lakeland Auto and Marine on identifying engine mechanical failures using electronic methods. My name is Amanda Goyette, and I am an admin assistant with AERA, and I will be in the background moderating today's event with my colleague, Rob Monroe.
Hey everyone, yeah, Rob Monroe here. I look after membership and technical development at AERA, and today you're in for a real treat. Chris Hamann from Lakeland Auto Marine, he's got a lot of really good information to share with us today, and we're looking forward to it. He is touching base on some stuff that's really going to open your eyes on some new school methods, on some old school engine issues. So looking forward to this one. More stuff that we've got on the go. We've got a busy spring actually coming up here. We've got 5 regional conferences that we're involved in all the way up through till June. So the first one that we've got is going to be March 15th at Liberty Engine Parts, and that's in Dallas, Texas. These guys always put on a first-class event, and looking forward to that one. Of course, there's at all of our regional conferences, there's technical presentations, there's lunch, there's a tour. There's always exhibitors there and vendors that have their tables there to talk to. But what's nice is these are a much smaller venue than what you would see at a large trade show. So you get a lot of great one-on-one time with not only the presenters, but also with the vendors. So make sure to have a look at what's coming up here pretty quick. After the March 15th one, we got April 25th at Chode Engineering in Bolivar, Tennessee. I've been talking to Cass on that one. This one's going to be good. He's not only going to have technical presentations, he's going to have some hands-on stuff going in the shop as well. So he's got a huge facility there, and he's actually going to have a bunch of equipment set up, and he's going to have components in the equipment, and they're going to be doing some hands-on stuff on that one. So that'll be a good one. Of course, May 2nd and 3rd, both Steve and I are actually going overseas on that one to head over to FTF machines, and they're an equipment representative over there that reps Rottler and Comic and Surdy. We're collaborating with them and doing an engine expo with those folks in the Netherlands on May 2nd and 3rd. So that's another one. Of course, June 20th, Goodson Shop Supplies. That will be another good one. They're turning 80 this year. So with Goodson, that's in Winona, Minnesota. And they had one several years ago. They put on another first-class event, so looking forward to that. And then last but not least, June 7th in Edmonton, Alberta, Canada, we're doing our own event at this one. Looking forward to coming to Edmonton to serve our Canadian members. And June 7th, the same thing. It's going to be 4 technical presentations. There'll be lunch. We've got a tour that we're doing with the OEM Cat Reman plant there. That'll be on the Friday. Of course, Saturday will be the technical part of it. I know Chris is going to be joining us on that one, and he'll be there with doing another presentation for us. So again, up in Canada, looking forward to that one. For more information on any of these regionals, just go out to our website. You'll actually see right on the home page, there's a regional tab there, and you can get signed up for any one of these regionals or get more information. So looking forward to seeing all you folks soon at any of these regionals. Chris has lots of information here to go through, and anybody that's met Chris, he was actually at our EPIC conference at PRI this year. He did a presentation, and you guys are in for a real treat. Chris is a good guy. He's going to keep you entertained, and he's from Lakeland Auto Marine in Port Clinton, Ohio. So, Chris, how you doing today? How's it going?
Excellent. How are you guys?
Excellent. Yep, excellent.
We'll go ahead and get the show on the road. Hey, thanks everybody. I appreciate you taking time today. My name is Chris Hamann. I'm here to present a seminar basically on identifying engine mechanical failures using electronic methods. So we're going to take maybe a non-conventional approach for maybe what you're used to, but I think once you find that when you learn how to do these methods, I think you're going to see that they're very beneficial. A little background on myself is our company, we've been in business 35 years this year. We've been an AERA member since '92. We got 10 people here. Our big business is car repair. We do have a machine shop. We've had a machine shop for probably 32 of those 35 years. But we specialize mostly in marine and industrial. We do some car engines, but most of it, since we're here on Lake Erie, we do lots of marine. I'm Mercury certified, I'm Volvo certified, ASE stuff. So, and recently I got into training over at EHOVI, which is a vocational school in Milan, Ohio, just by Norwalk Raceway Park. And I started doing, creating our own marine training using the picoscope, which is specifically what we're going to talk about. because in this marine world, we see a ton of mechanical engine failures because these engines work so hard. And I see a lot of people get tripped up. And so we've got 21 shops that actually have bought scopes and that have attended our training, and a bunch of people from all over the country, believe it or not. So that's a little background on me. There is my contact information down there. So you're welcome to email me with any questions or anything you may have on these presentations or anything I've got. So without further ado, let's jump right into these goals I've got here. So my main goal here is I want to introduce you to picoscope and its advantages versus traditional testing methods, okay? When I say traditional testing method, I'm talking compression gauge, vacuum gauge, you know, stuff like that. I don't use compression gauges anymore. I know that sounds corny. You're probably thinking, how do we fix anything? But a compression gauge is so limited, okay? It only does me one thing. It just tells me the cylinder's ability to seal. That's it. Doesn't tell me if it's breathing. I can't tell anything about anything else. You know, I got a Schrader valve in there that traps stuff. When I use a pressure transducer, you know, we don't have any of those problems. All right. And we're going to use starter current, and I'm going to get to that. But I've picked out 4 tests for today that I want to talk about. And that is relative compression, cranking vacuum. We're going to do a little bit of crankcase pressure testing. All right. Because I can actually use a pressure transducer to figure out what cylinder has pressure in the crankcase. So I got a guy that's got a chipped up diesel truck, you know, he's got the Banks power, all that stuff in there, cracked a piston, and, you know, maybe it's got a misfire code. You know, I do an old school crankcase test and I got pressure. That doesn't tell me what cylinder, okay? With this, I can tell exactly what cylinder, and I'll show you how I do that. I got one example. And then I should have time, I'm gonna get to in cylinder. I know we dubbed this as, you know, zero disassembly, which most of it we can do without any disassembly, but at times we do have to remove a spark plug and go in with a pressure transducer and get some data there too. So, but my goal is I want to determine engine mechanical integrity accurately, okay? And I want to do it quick. You know, sometimes we get beat up. When I see technicians, I see issues where they start putting distributors and injectors and computer software and all that stuff. And, you know, I was taught years ago, and this has always stuck to me, is you can't tune a sick engine. And if I got a sick engine, no compression, breathing problem, there's no parts I'm going to bolt on that thing that will make it work, okay? So in my opinion, when you have a tough drivability situation, I always want to either go or no go the engine mechanicals, okay? And I want to do it quick, and I don't want to do a bunch of disassembly. I don't want to take valve covers off. I don't do any of that stuff. So I've got a few case studies of some cars and boats. I'm going to drive this thing home. Now, things used to be like this, right? A monkey could do some stuff. You know, I know we're kind of poking fun here, but, you know, we used to be able to get by with a vacuum gauge and a compression test. But that's when engines were simple. We had 2 valves, 1 camshaft, everything was kind of the same. Well, now you've got, you know, you know, you've got cylinder deactivation, you've got multi-cams, you've got variable lift. There's all kinds of stuff going on in modern car stuff. But here's what I want to know fast, right? I want to know sealing. I want to know breathing. I can check base ignition timing, okay? I'll show you how we do that. When I go in cylinder, I can identify where my exhaust valve opens, we call it EVO, and I can identify where my intake valve closes, okay? I can also determine if I have an exhaust path restriction. I've got an interesting case study I'll show you where I have an exhaust restriction, okay, on one side, and the car did not run right, okay? And you would think it has a mechanical problem, all right? And I'm going to go in and I'll show you, like with cranking vacuum, how we can tell if I have a V-type or multi-bank engine, if one side is breathing differently than the other. You'll see me use that in action on actually an engine that we put in from a reputable reman facility. You know, just because it's new, don't mean it's going to work, right? Because you know what new stands for? Never, ever worked. So what am I using here, right? Well, we're going to use an oscilloscope. Now, some of you guys may know what a scope is, some don't. I'm just going to give you a light touch on this, okay? So basically a scope is we're going to measure voltage over time, all right? Now, the equipment we're using and the equipment I like to use is I like to use Pico, okay? I think they do a fine job. This is not a commercial, but I just want to tell you what I'm using and why I use it. And as of today, I just went to Pico's website, and that's the cost of a 4-channel kit, okay? And it's about $3 grand, and you want a 4-channel scope. I know there's guys that look at 2 channels and that, and 2 channels are okay, but you really want a 4 if you're going to spend the money. And this pressure transducer, which to me is what really makes this tool. This pressure transducer, in my opinion, is arguably the best piece of this Pico system. I can't tell you how much I love this. I mean, this thing is unbelievable. You're going to see me stick this in all kinds of places you didn't think you could stick anything, okay? But it's about $1,200 too. So you got a pretty significant investment here, and you definitely need training. This is nothing you're just going to buy this stuff and go to work tomorrow. It's taken me years. I've attended lots of training from very, very smart people on how to use this. And in fact, all these tests I'm going to show you today, they're not my tests. They're all tests I've learned, okay? The only thing I've done maybe is just apply it to marine, which nobody seems to be doing at this point. There's a couple outside vendors. Again, not a commercial. You can buy it Pico Direct, or you can deal with AES Wave, a fine company. You can deal with CAS in New England. CAS is actually where I buy a lot of my stuff from. Again, not a commercial, but these are good resellers that also have tech support, okay? So if you buy from one of these guys and you got issues, they're very good at tech support. They both have great departments on that. So why do I want to use the scope? Why do I want to invest this money? What's my end game here? Well, you know, scopes don't need updated per se. Okay, you know, if I buy a scan tool, I got the fresh new Snap-on, Mako, whatever you want to call it. You know, there's always an update fee. Things are always changing. Well, voltage over time really hasn't changed. Okay, so all I'm doing, and with the software updates that Pico has, most of them are free. In fact, all of them are free. You know, they're constantly refining. They're adding phase rulers, which we're going to talk about, math channels, which we're not going to talk about. But you know, they have all kinds of interesting features that they keep adding. Okay, this tool is an OEM tool at every GM dealership. It's at Tesla, it's at Mazda, it's all over the place. Now GM, they just use it for their NVH, which is actually pretty phenomenal too. That's noise, vibration, and harshness. That's what they got it as. But these GM dealers, if the service manager or owner or whatever would order one more part number, they would get everything that I'm going to show you, okay, with the amp clamps and when they need to order a pressure transducer too. But they actually have the power that I'm going to show you today in every GM dealership, and most of them don't even know they even got this thing laying there in the back room. So if you don't have Pico, you can download the software for free. I'd be glad to send you some files. You can play with it. You know, like I say, it does have a learning curve, but I don't think it's insurmountable. All right. And the key here when you scope is you've got to look at good engines. You know, the number one thing I see people make a mistake is they go out and they grab a scope, all right, just like this Pico right here, this 4425A, and they got this job that's kicking their butt, and they think that this scope is going to be the savior. Well, it can be the savior with a qualified operator, okay? This is like drinking wine, right? It's an acquired taste. You have to frickin' start using it, okay? If you think you're going to dig this out and be Johnny on the spot right out of the gate, you're going to be sadly mistaken, I can assure you. So start looking at good stuff, right? You got what I do here in the shop. I get new cars in, new engines I'm rebuilding, something like that. I hook it up. If it's an engine I've never seen, I'm getting cranking vacuum. I'm going in cylinder. I'm getting all these valve events, right? Because if I don't know what good is, how do I know what bad is? And none of this stuff, or very little of it, is in service information. So it's always best to create your own database. I cannot stress that enough. There's always a goal when you're diagnosing something. I don't care if it's a human being, I don't care if it's a veterinarian, whatever. The goal is I want to figure out what's wrong without taking it apart. I feel like once I take something apart, I'm in resolution mode. And resolution mode sucks, okay? There's nothing worse than thinking, oh yeah, I got a bad cam, and you spend an hour tearing a valve cover off and find out it's not bad, okay? Or you slam dunk a fuel injector in or a coil, or you do swap gnosis, right? Where you move injectors and coils around and do all that stuff, swap oxygen sensors. You're going nowhere, you know, and it's hard to build for that kind of stuff, you know. I feel like I can build diagnostics, you know, if it's done correctly. So that's our goal. So the question here I have is, what is relative compression? Well, it's simple. It's a test that we're going to measure compression, we're going to measure starter current in relation to each other. So the theory is if I have, let's say, a V8 engine, all right, and I have all 8 cylinders that have the same approximate compression, the starter motor should work equally as hard on every cylinder. So let's say the starter peak current is 211 amps. If I have 8 8 humps of 211 amps, I can infer that everybody has the same compression. Now, I don't have a number, whether it's 160 pounds or 210 or whatever, and I'll show you how we get around that here shortly. But I can at least pick out somebody that's not like the other one, okay? Which to me is quick. If I can identify, hey, I've got 7 current peaks that are very good, and I've got 1 current peak that is very low, now I know I'm probably chasing a mechanical concern. That's something I need to go after, okay? Without doing a bunch of screwing around, because who in here wants to tear out 8 spark plugs, all right, and do an old school compression test? It takes, depending on the application, could take an hour or better. Some of these cars, you got to take intake manifolds off or take wiper cartridges off. Who wants to do that? Not me. I don't want to do that anymore. I'm getting lazy. We're going to graph the starter motor current. Okay. The other thing we can do is we can check the starter. We can check the starter's integrity of the starter motor. Okay. And I already talked about if I got an old school engine with a single camshaft, you know, for instance, if I have a timing chain that is 1 tooth off, okay, on a single cam engine, let's say it's an old small block Chevy, everybody is going to be affected, okay? So, but when I have multiple cams, you know, only one side potentially could be affected if it's a V-bank. So let's say I got an exhaust cam that's off on one V-bank side. It's gonna, you know, I'm going to have 3, if it's a V6, I'm going to have 3 cylinders that have different readings potentially than the other 3, all right? And I'll show you how we get around all that. So that's basically how we're doing this. We're going to quickly determine if we got to go or no go or go inside of a cylinder. And we're gonna check ignition timing here pretty quick. All right, I'm gonna show you when the spark line happens at the current peak. You know, if I've got a reluctor wheel that's possibly moved on a crankshaft, this is a great way to figure this out. Okay, we all know LS engines, for instance, there's no timing marks, there's no keyway in the balancer. You know, I haven't seen it personally in LS reluctor wheel move. I've seen reluctor wheels move in other engines, specifically the 3.6 GM, and this is how we find them. Okay, but again, go, no go. And this is a test I want you to get in the habit of making. Let's get going, right? I got a lab scope. I got a high current probe, okay, that we're going to place around a battery cable. And I want to get a spark event. The reason I want to get a spark event is we always know when spark happens, right? It's got to happen at or around TDC. You know, we never go off a fuel injector or anything else because we have no idea where an injector fires. But I do know when the spark plug fires. So I'm going to time these starter peaks based off of a ignition event. All right. So then I'm going to input my firing order. All right. If I don't have old school plug wires, I can use a current clamp on a coil. And I don't even necessarily care if it's number 1. You know, if I'm working on a car and let's say number 1 is buried behind an intake manifold, I'll grab somebody that's close to me. I do this on boats, right? I mean, if I'm on one side of the engine, I'll grab the side I'm dealing with and grab that plug wire. If I'm on plug wire number 5, I can fill the firing order in from there. You know, I don't necessarily have to get on 1. I do recommend for new users to get on 1 because it's easier in your head. Okay, but I got to have a trigger, right? Whether it's a plug wire, you know, a coil turn on signal or something like that. And here's a picture of what I'm going to be using, right? I've got an old school inductive plug wire probe, and I got a high current clamp that's going around a battery cable. The technique I'm going to do is we're going to disable the engine from starting. I just want it to crank, and I want it to crank for about 5 to 10 seconds. The longer, the better, because I want a cluster of data. I just don't want to crank the engine and go, no, I want to see repeat, right? Do I have something that seems to be repeating? Okay. Couple prerequisites here. You've got to have a stable cranking speed. You know, if this battery is junk, it's been on a charger for 3 days and it's 10 years old, you know, if I don't have a good starter and stable cranking speed, this test is useless. Okay. So, you know, a lot of times these cars come in, the battery's dead, somebody's already been messing with it. You know, if I'm going to use this test to my advantage, it's got to be stable. Okay. And I don't care if it's the negative cable or the positive cable that I connect my current clamp to, because whatever current leaves the battery has to come back. So if the ground cable's staring me in the face, that's fine. I'll line up the cable and go from there. All right. So, and I just got to make sure that I'm getting the starter motor current. I'm not on a fuse box wire or something like that. So we're going to go to number 1 plug wire for all these case studies here for easy. And like I said, I don't necessarily have to go to number 1. First thing I want to do is look at known good. I've got a Crusader 350. This is a marine engine. All right. And you see I got my probe on number 1. All right. I got my Number one here, I got my inductive pickup, okay? And I've got my battery cable, right, going to my battery, and I got my amp clamp going around that, okay? So that's my initial hookup here. I got to find a battery cable and an ignition event. That's all I'm doing, okay? And I'm disabling the engine from running. So this is an EFI engine. I just disconnected the fuel pump. You know, on some cars, I pull fuses, I pull relays. You guys are mechanics, okay? I'm sure you can figure out a way how to make an engine not start and still crank and still have spark. I want spark just so I know how to identify. I don't necessarily have to get spark right away. I mean, I suppose if I just use this battery cable and I crank this engine over for 10 seconds, everybody looks the same. I don't necessarily care who's who, right? I mean, if they're all the same, I'm not necessarily need to know how to identify who's what, you know. On my scope, I'm going to set to at least 1,000 amps per division on the starter current side. If I got a carbureted engine, I got to run the carburetor out of gas. Okay, there might be some leftover fuel in it. It may want to start, but I'm going to continue to crank this thing till I get some good, you know, if I get 5 to 10 seconds of stable crank speed where it's not trying to start, that's enough data that I can make some analysis here. And I have a number here that I learned, and that is I'm looking for 35 amps peak to peak. And I know this seems weird here until I show you some patterns, but between the peaks and the valleys between the cylinders on a gasoline engine, I'm looking for a minimum of 35 amps, okay? So if I don't have 35 amps peak to peak, I could maybe have, on everybody, maybe I could have something out of time. Like maybe I got a single cam engine that the timing chain is jumped, or I've got an engine that the cylinders are washed with fuel or something like that, okay? Where it's washed out, doesn't have any compression, all right? So let's look at this known good so I can explain this better. This is my initial Pico screen, okay? My horizontal axis is time, okay? And we are 10 milliseconds per division, all right? And in this case, and voltage is going to be my vertical, all right? So voltage is this way, time is this way. Now, here's my first capture, all right? Here is this is that 350 Chevy Crusader, and I disabled the fuel and I rolled it over for about 10 seconds. I've got 5 seconds of division here. I know that may seem like jargon at this point, but I think you'll follow me where I'm going. And my red is my number one spark event, all right, on that plug wire, and my blue is my starter motor current, all right? Now this looks like a big blob right now, but one of the things I like about Pico so well is their zoom feature. I can put a bunch of time on the screen and then I can zoom in. And that's what this little magnifying glass is here. So I'm going to use this magnifying glass and I'm going to blow up, as I call it, a certain section of this. So I blow up a section of this and I'm looking for anomalies here. All right. And I'm looking at this thing and I'm like, looks pretty good. All right. I see some firing events here. I got a little bit of interference, but that's okay. We'll get around that in a second. But main thing I'm looking at is my starter motor current. And you can see here, I've got some humps. All right. They look pretty even. Now, this is an engine that has nothing wrong with it, so I expect it to have, nothing, I expect it to look even. So the next thing I'm gonna do is I'm gonna grab some horizontal cursors, and that's what this box is right here. And I'm gonna grab a horizontal cursor and drag it down, and then I'm gonna grab another horizontal cursor and drag it on the bottom of this, because I wanna measure my peak to peak amps. And I did that right here, and I highlighted it in yellow, and the software automatically tells me, hey, Chris, I've got 57 amps. And you know what, 57 amps, I'm happy with that. It's over my 35 for my gasoline engine. And it looks like everybody is touching the line. Looks like my peaks are absolutely gorgeous. And that's what I'm looking for, okay? I don't see any anomalies at this point, all right? I'm gonna blow this up again to get one 720-degree capture. All right, so obviously for a cycle, the crankshaft spins twice, 360 degrees in a circle, 720 degrees total. So here's my number one firing event. All right, here's my number one firing again. So this is 720 degrees. All right, so now I can input my firing order. So it happens to have the very popular 18436 firing order, right? So I plop that in, and now I have identified each cylinder. All right, each cylinder's starter current peak. Well, if I had a cylinder that wasn't sealing very well for whatever reason, you can pretend leaky intake valve, hole in the piston, whatever, I am not going to draw the same amount of current here. okay? And that could allude me to, hey, Chris, you've got a mechanical problem here. I need to go chase this. So this looks pretty good. I don't see anything. Now, it's taken me a little bit of time to explain this, but I think you'd agree, I don't have much time invested in this, right? I think the hardest thing I had to do was figure out how to disable the fuel, okay? And I know that every cylinder is relatively the same as the others. Now, this is one thing I really like about Pico, and they use phase rulers, all right? And phase rulers, I can actually identify all of the 700, I can identify every ounce of the 720-degree cycle, all right? So I'm gonna open up this rulers box here. I'm gonna turn phase rulers on. I'm gonna select 8 partitions since I'm a V8 or an 8-cylinder engine. So 1 partition per cylinder, and it's gonna pop up down here, these little arrows. Actually, I'll go back. And I'll grab these arrows and I'm gonna line these up with my #1 firing event. So I've jumped ahead here and you can see that I've taken this and I have lined that up with the beginning of my #1 firing event, which we'll call 0 degrees, and my last #1 firing event, which I'm gonna call 720. And you know what? You see how this is a darker blue than a light blue, dark, light, dark, light. You see how I have a firing event just about at the transition? That's what I'm expecting, right? I mean, 720 divided by 8 is 90. So I expect a firing event every 90 degrees in this thing, all right? And that's exactly what I have, 1, 8, 4, 3, 6, and so on. So this is very, very handy. I love these phase rulers. You're gonna see me use these a lot here coming up. The next thing I can do is I can plot my ignition timing. Now, this is not the same as the timing light. It is very, very close, okay? But let's say I got a spun balancer, or maybe I've got a reluctor that's moved. This is something I can do very quickly to figure out if I'm right or wrong, or I'm in or I'm out, okay? So I've taken vertical cursors, all right, which I'll go back right here, okay? This little box here that's kind of cut off. I'm gonna grab a vertical cursor and I'm gonna put him at the 0 degree mark, all right? And then I'm gonna grab another vertical cursor and I'm gonna put him at the high peak of that #1 current, because that highest starter current peak is actually TDC in the cylinder. You know, think about it, that piston's going up in the bore, right? The starter's gonna draw the most current at the highest compression. Well, that's gonna be right where the piston goes all the way to the top, right? Piston's coming up, as soon as it gets here and that rod swings over and goes back down, that's TDC. It's not a degree wheel. I'm not suggesting that it is, but it gives me an idea, hey, is my ignition timing relatively close to where I'm expecting, right? That's what I'm looking for. So I plot these in, and this thing actually is firing at 4, almost 5 degrees after top dead center. And on this engine, that's pretty normal, because on this marine engine, this has that HVS, that world's worst distributor, the flat cap GM, okay, total trash. It's an ATM machine for me. I love that they make them. But this system here, the spark is done off of the crank sensor, okay? So that HVS has nothing to do with base ignition timing. So based off the crank sensor and the programming in the computer, these 350 late model engines love to run at timing retarded at 4 to 10 degrees at times, okay? Especially the catalyst motors. So it's not uncommon to see this. But if I'm working on a 57 Chevy, I'm working on a race motor or something like that, on a dyno cell, and I know I got the timing at 10 before, I don't expect this here, okay? That's not where I expect. I do expect it on this application, okay? I just want to know where I'm getting this information from. So does that make sense? That's a quick rundown on relative compression. I'm now going to jump to cranking vacuum. We're going to look at known good here. So I've got this pressure transducer, right? And I'm actually going to stick this in a PCV port, all right? And I'm actually going to look at intake manifold pulls. And what I mean by pulls is I can look to see each individual cylinder, how well he pulls vacuum compared to his neighbor or somebody else or the rest of the engine, right? So if I got a wiped cam lobe, I've got restricted exhaust, I've got timing that's off, you know, this is a good test that can tell me that. So here's a quick rundown on this 500X tool, right? Awesome tool. It takes any liquid. You can put fuel pressure, cranking compression, You can put oil pressure, transmission pressure. You can put it in cooling systems. If you go on YouTube, you'll see where guys actually put this in a radiator cap, and they'll start an engine up, and they can identify head gasket failures to specific cylinders. You can take spark plugs out and crank the engine over, run it. If the pressure doesn't build, you know it's that cylinder. All kinds of stuff. This tool, it has a range from -15 psi to 500 psi, and it holds a zero line that's unbelievable. This thing is just definitely accurate, you know. And that's one thing about a vacuum gauge. You know, vacuum gauge is a good tool, and I still use them from time to time. But a vacuum gauge isn't corrected to atmospheric pressure. You ever notice when you get a vacuum gauge how that zero line is about as wide as my head, right? Because they don't know where you're at. I could be in Denver, Colorado. I could be in the equator, right? I mean, so, or I could have a thunderstorm or some kind of issue moving in, right? So zero is always a, you know, a gray area. Well, with this tool, zero is not a gray area. When you turn it on, it does a self-calibration and it's zero, believe me, okay? So it's very accurate, which is what I like. So here's how I'm going to do cranking vacuum, all right? Same basic setup as relative compression, and I normally do both these together, okay? I usually do relative compression and cranking vacuum on the same screen. Do the same thing on ignition. I'm looking for the most centralized port, all right? I know some engines, we got brake boosters, and brake boosters are going away on modern cars because we got electric brakes, I know. But I want the most centralized port I can find. All right. I don't necessarily want to be on number 7 intake runner. And for you old school guys, you're talking old big block Chevy, old small block Chevy, they had that 3/8 pipe plug on number 7 intake runner that's been in there since 1962. I ain't taking that thing out of there. Okay. By the time we get the torch and try to get that plug out, we could already have the diag done. I mean, I can find a choke pull off hose on the Quadrajet or the Holly or something like that, you know, or a modern car. Like I say, I'm using a brake booster or PCV or something like that. But I'm trying to get the most centralized port because I don't necessarily want number 7's intake runner because he might pull a little bit more since I'm closer to the intake valve on that. But if I got a centralized port, I'm going to have a better analysis. Okay, I'm going to look at everybody. You know, everybody should look very similar at that point. All right, same thing. And guys, this is the only time you want to keep the hose as short as possible. All right, you're allowed to here. Because if I have a longer hose, and specifically, I love to use spark plug boots. You'll see on my pressure transducer here that the spark plug boot is the star of the show, okay? Because I can jam this thing over anything. I can turn them around, okay, and go like this. And I got a smaller hole here to go into a smaller port, okay? And this is very, very short. If I got a really long vacuum line, okay, that can dampen my reading. Okay, if I got a vacuum line that's 2 foot from the intake manifold to my transducer, he could take some dampening out. I want to see the change in vacuum, which I'm getting to. So the shorter the better. I'm going to crank the engine over for 10 seconds, and there's some modern outboards and some modern cars that you can't get to vacuum. If you have an old school traditional map sensor, I can back probe that map sensor and get a very similar pattern. I may not have the resolution that my WPS 500X has, but I can get the job done, and I've done it in the past. I can think of a 150 horse Merc outboard that has no PCV, no access, okay? And the map sensor bolts directly to the intake manifolds, not on a hose, right? And that map sensor stares me in the face, so I just back probe the signal wire, okay? And I get a very similar signal. You can do the same thing. Here's my technique. I'm curious about the shape and the amplitude of these pulls, and I'm going to show you here coming up. But the two things I can measure, all right, is what I'm interested in is I'm interested in the change in the vacuum from cylinder to cylinder and the rate or the speed that it changes between cylinders, okay? You'll see when I got some case studies coming up here that we're going to have some abnormal vacuum pulls, okay, which is going to make me, you know, start to consider like, hey, maybe I got something going on in this cylinder or another cylinder, okay? But that's what I'm after. All right. I know there's another tool out there made by Cenex. It's called the First Look. It is also a very good tool. I used to use that before Pico came out with this. The only difference between the Cenex First Look tool and this, well, one big difference is that can't tell me the actual vacuum level. Okay. It can tell me the rate and it can tell me the speed of the change. Okay. But it can't tell me the actual vacuum in the intake manifold. This thing can. Okay, so that's why I use this more over my Cenex piece. We're going to trigger off a cylinder again. We're going to divide the pattern up into individual events, okay? And one thing to note is the intake, if I'm triggered off number 1 cylinder, for instance, that intake pole is going to be 360 degrees from the trigger point. So like with relative compression, like when I was tied to number 1 and I was looking at number 1 starter current peak, that was number 1. Well, in vacuum world, you got to think, right? I'm not on the intake stroke when that cylinder is getting ready to fire, right? It's 360 degrees after the overlap, okay? And I'll show you how to figure all that out here shortly, but I just want to make that comment, all right? I want to identify each pole, and the deepest vacuum with this tool is going to be at the bottom of the pattern, okay? And I always set, there's 3 ranges on this thing, okay? And I like using range 3, which is -5 PSI to positive PSI, or positive 5 PSI. Now, I don't know about you, I'm an inches of mercury guy, okay? So all you got to do is multiply it by 2. So -5 PSI is going to be 10 inches, okay, of mercury. I got this Crusader 350. I got my WPS 500X. I jammed it into a PCV hose. You see, I disconnected the PCV hose here. It's going underneath the coil and stuff. I got this thing on range 3, and I'm ready to make some analysis here. So I cranked this thing over. The engine actually wanted to start. Green is my vacuum, red is my number 1 plug wire. And you can see when I first started, this thing actually pulled down and then it came back to normal and I got some cranking. The reason I put this in this capture in this presentation is this is real world. I don't want to show you, exact perfect every time, because in the real world, there's always some fuel left over, or the temperature of the engine. If you're doing this thing hot, which you should be doing, okay, you always should be evaluating these engines at operating temperature. But I want to know, hey, this thing started, it's okay. I'm going to continue to crank it, and I can still see I can still get some analysis over here. So let me zoom in. I'm going to grab my magnifying glass, and I'm going to zoom into this part right over here. And I pull into this part right here, and I'm looking for a couple of things, right? Remember I said my deepest vacuum is at the bottom? And I grabbed a horizontal cursor and I drug him down, okay? And he's looking at all these pulls. Now, I don't know what cylinder's what yet, but do I necessarily care, right? I mean, this is number 1 firing event. This is number 1 firing event. Let's count. We should have 8 pulls. 1, 2, 3, 4, 5, 6, 7, 8. Repeat. These pulls look beautiful. I'm sure you would agree that these pulls all look the same to each other. This is what a perfectly sealing and breathing 350 Chevy looks like, okay? This is what I'm looking for. I got two-lipped intake valves. I got a bad cam. I got restricted exhaust. 9 out of 10 times, I can find it right here, okay? I can find it right here. Now, I'm going to show you how we're going to decipher this in a second. But if I see this, I know I don't have a mechanical problem, okay? And this is what I use and when I coach our guys in our shop, okay, is we got a car comes in, let's say it's got a misfire, right? Or maybe it doesn't idle right, all right? I go right here, right? And if I get a good cranking vacuum pattern like that, I know that I'm sealing and I'm breathing fine, okay? Then I probably have a problem that's outside the engine. And that's key in diagnostics, right? Because if I know what it isn't, sometimes it's good enough as knowing what it is. And this is go, no go for me, right? I see this, I'm moving on. Now, we need to decipher this. I have a tool that I use. Again, this is not a commercial, all right? But this is a friend of mine, Scott Schotten. He has a company called Drivability Guys, all right? And for 20 bucks, you can give him 20 bucks. He will give you these, what we call piston position charts, all right? And when I make an analysis on a cranking vacuum pattern, I need a piston position chart because I need to know what's going on in other cylinders at the same time. And the reason I say that is when you have a V8 engine, for instance, there are 3 intake valves open at the same time, right? One's starting its intake stroke, one's in the middle of its intake stroke, and one's ending its intake stroke. So that means if I have a problem in a cylinder, potentially 3 other cylinders, vacuum pulls could be impacted. So where this kind of can get tricky is you might say, hey, wait a minute, I got low compression on cylinder 1, but how come cylinder 5's intake pull's impacted? Okay, there's actually nothing wrong with cylinder 5, okay, but this is why you need this piston position chart. This is what it kind of looks like, all right? I just put a simple 18436 firing order in here, all right? And how I read this is, I'm going to show you here in a second when I put this on a pattern. Let's say I have a pattern, or let's say I have a vacuum pull issue right here. I look up right here, right? And this tells me what's going on in other cylinders and in that moment in time, right? So obviously when number 1 fired, number 8 is finishing its compression stroke, number 4 is, on its way in its compression, number 3 is intake, and so on and so forth, right? So this is how I'm going to determine, what to chase in looking at a cranking vacuum pattern, right? I got to know what's going on elsewhere, okay? I need to know that. It's very important. Here's how I deploy this thing, right? I pay the 20 bucks, I get this software, I fire it up, I get this menu, all right? First thing I need to do is I need to choose my firing order. And he's done a nice job, and most of the time, your firing order is going to be in here. So I picked my firing order, 18436-572. I tell it what cylinder I'm syncing on. In this case, I'm on cylinder number 1. If I'm on cylinder 5's plug wire, I'm on cylinder 3's plug wire, or whatever, a coil, I just go up here and say, hey, I'm going to sync on number 3 or wherever I'm at. Then this thing pops up, all right? And this is adjustable. And you see I've got my scope pattern here, and I'm going to drag this with my mouse. I'm going to left click it, I'm going to drag it in position, and I'm going to drag it so the right end of this is up against my number 1 firing line over here, and my left end of this is up against my number 1 firing line here, okay? So I'm going to expand this piston position chart over 720 degrees. And this is what I've done. I've got this thing lined up. Now I can identify stuff. All right, and remember what I said, number 1's intake pull is 360 degrees from the firing point. Well, this happens to be 360, right? So see, number 1's intake pull. This is number 8's intake pull, okay? And so on. So I can go 1, 8, 4, 3, 6, 5, 7, 2, 1, repeat, okay? I know I didn't put the numbers in here just quite yet, but I will coming up. But this is how I know what to look for. And let's say I had a problem right here. This is where I'd go right to this section of the chart and say, okay, who's going on in what other cylinders, right? So I'm going to use this chart to determine that. I'm going to make a couple points here. And this is typically, this is not on always, okay? So this goes back to my 7th grade science teacher, where, I failed a question, and I'll never forget this to the day I die. And the word started with all, or the question did, right? It says, I forget what the rest of the question was, but it said all blankety blankety blank. And I had marked that true. And Mr. Link looked at me and he says, Chris, I've got news for you. He goes, anytime you see a true false question that starts with the word all, mark it false. Don't read the rest of it, just mark it false. And you know what? I lived and died by that. So that's why I use the word typically here, not all, typically, all right? And typically, a leaking exhaust valve, okay, is going to show up on that cylinder's intake stroke. And let me explain. So let's pretend number 1 cylinder has a burn exhaust valve, okay? Well, when the intake valve opens on cylinder number 1, now my pressure transducer is now connected to cylinder number 1. It's connected to a couple other cylinders too, but it's connected to number 1. If I've got pressure in the exhaust, okay, excuse me, when the exhaust valve is, let's say it's got a hole in it, tulip, whatever. Now pressure is going to bleed into that cylinder, and that could have an impact on the intake pull of that cylinder, plus other cylinders while that number 1 intake valve is open. Because as long as that number 1 intake valve is open with an exhaust valve leak, he could bleed exhaust or bleed pressure into my intake manifold at that time. And then as soon as the intake valve closes, if I see the vacuum start to dip down, those are clues. Okay, those are clues to what's going on. Same thing like if I had a detonated piston. Okay, if I had a hole in the piston, when the intake valve opens and there's a hole to the crankcase, that's when I'm going to see the intake manifold pressure almost go to atmospheric. And as soon as the intake valve closes, that's when the vacuum will start to drop. Typically, an intake valve is going to show up on the companion cylinder. Okay, so 1 and 6 in a Chevy generally is our companion cylinders. But I like to look at it this way. An easier way to look at it is I'm going to have a loss of vacuum or an increase in pressure in the intake manifold just before the leaking intake valve cylinder fires. So for instance, if number 1 has a leaky intake valve, when the piston's going up on compression, he's going to blow a little pressure, depending on how bad the leak is, into the intake manifold, okay, on the compression stroke of that cylinder. You know, we can't ID valve leakage when those valves are open. I know it sounds crazy, but, you know, a valve can't leak when it's supposed to be open. We have to evaluate valves when they're supposed to be closed, right? That's why we evaluate the intake valve on the intake, the exhaust valve on the intake stroke, and we evaluate the intake valve on that cylinder's compression stroke, generally, or the companion cylinder, same thing. So we got a little crash course on how to do this, so let's put this to work, okay? And my first culprit, the case study, is going to be a 2002 23-foot Sea Swirl. All right, it's a boat. I know maybe you guys aren't boaters or whatever, but that's okay. And I'm there because a friend of mine wants to buy this boat, and it's a pre-purchase inspection. All right, and he says, "Hey, Chris, will you come out and check this thing out before I buy it?" I said, "Sure, I'd be glad to do that." Okay, and I did this last July at a local marina here in Port Clinton, where I'm from. It's carbureted. There's no hour meter. You know, we're just kind of checking this thing out, right? So I go down to the marina and I start this thing up. The salesman's there, and this thing had a quivery idle. And another comment I want to make right now is when you have cylinder leakage, typically it's going to show up at idle or low speed because a valve is closed longer at low speed than it is at high speed, right? I mean, this is why I like cranking vacuum so much. I can tell 99% of the time if I got a leaky valve cranking. I hardly ever do it when it's running because things are happening too fast. It's a little bit harder to decipher and analyze. And when it's running, the valve is not closed as long. But when I'm cranking and the valve is closed longer, it gives me more time to evaluate it, and that's when it's supposed to be closed. Okay, so this thing has a quivery idle, and I could hear it missing, right? And of course, salesmen, they don't know anything. You know, I'm not picking on salesmen, but he's like, "Oh no, this boat's good to go," blah 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 blah, right? One of the first steps I do, all right, I'm not playing any videos. This is a case study I stole out of my Marine class, is cranking cadence, okay? And I can't tell you how many engines that I can KO by listening to how the starter sounds, right? Pull the coil wire, do something stupid, pull the fuse. A lot of cars, you can put the throttle right to wide open throttle, clear flood mode, right? Shuts the injectors off and crank that engine for 5 to 6 seconds. You know, it goes something like that. Sorry, I'm not trying to be Jones off Police Academy, but I'm just trying to give you an idea here. But when you hear that cranking cadence like that, and you hear that anomaly of the starter, somebody doesn't have compression, right? So I do that, and this thing doesn't sound right. So I look at my buddy and I said, "Hey, this thing's got a cylinder down." So I go right to my truck, I grab my scope, all right, and here I'm at. Now, would you agree? How many volunteers do I have that want to do a compression test on this thing? Okay, first of all, he doesn't own the boat, all right, or not yet, all right. Turns out he ends up buying it, but we'll get to that in a minute. But does anybody want to go down here and rip 8 spark plugs out, right? Half the time the boots are stuck to the plug, right? Nobody puts dielectric grease on them. All of a sudden, now I'm putting spark plugs in it. Now I'm putting plug wires in it, right? We got some money invested here, right? I want to knock this diag out, right, without taking it apart. That's my goal. I want to know who's out and what could be a potential cause. All right, so that's what I'm doing. This is a carbureted old school 305 Chevy, right? So again, not easy to, where's my knees, right? My knees are gonna be right here. Look at that, there's a latch there. I can already feel the pain in my knees sitting here trying to get these plugs out. Ain't happening. Let's practice what we preach. I run the carburetor out of gas, I disconnect the fuel pump, I start the engine, I let it run out of gas, and this is what I got. I crank it over, and I crank it over for about 8 seconds here, right? I mean, there's 3 seconds, there's 8 seconds. I already see an anomaly here, right? I see blue is my starter motor current. Let's just focus on that first. I see some vacuum stuff here too, but whatever's going on here, I'm sure you would agree, repeats, right? And I put these yellow boxes up because these are places of interest, right? I look at this as a crime scene, right? This is CSI Port Clinton, right? I'm trying to figure out what's going on here. And I see this, I put these yellow boxes up here and I see this dip. I see this dip, dip, dip. Somebody don't have compression here, all right? No doubt, right? And I got something going on with my vacuum. So let's figure out what's going on. So let's bring my phase rulers in. So I zoom in again to 1/720 degree section, right? So I deploy my phase rulers. I showed you how to do that earlier, and now I can kind of get a visual of who's who, okay? So let me put the numbers in for you, make it a little easier on your eyes, right? 18436. Well, guess what? Cylinder 7 doesn't look like he's doing anything, does it, right? Would you agree that 184, it looks like 4 might be a little bit down, 3 might be a little bit down, not horrible, okay? Now, you might look and say, well, Chris, 2's a little bit higher, but you got to remember, number 7 doesn't have much compression evidently here, right? So what happens when you have a cylinder that doesn't have any compression? Doesn't the crankshaft speed up a little bit, right? If this thing is rolling over and all of a sudden it gets to a cylinder that it doesn't have as much, that starter didn't work that hard. Now, the crankshaft speeds up for the next cylinder of the firing order, which is 2, and that's why that current is just a shade higher. That's actually kind of normal after you have a situation here. Because let's say I didn't have these numbers. Let's say it's my first day on the job. All I got to do is count and go 1, 2, 3, 4, 5, 6, 7, 1, repeat. I've only got 7 current peaks. I know this is a V8 engine, right? So something's up. So 7's my guy. Now, what I want to know is what's wrong with 7, right? We know 7's it, all right? And we got a couple other questionable characters here, but not so much, but this is my guy, right? Well, now let's deal with this vacuum pattern. So I'm looking at this vacuum pattern, and I already showed you good, right? So I'm looking for 8 poles, right? Maybe that's a pole. That could be 2. That's definitely a pole. 3, 4, 5. Not much of a pole here. 6, 7. So I got maybe 2 or 3 quote unquote good poles. We'll call them intake poles. Okay. And then I've got some poles here that really kind of aren't doing anything. And this is why I like cranking vacuum, because I can tell if this thing is sealing and breathing well. And we obviously got a cylinder down. Okay, we know that. But my point here is we've got maybe 5 minutes invested in this job. Is a new coil going to fix this boat? Is tuning it up going to fix this boat? Are 2 cans of Seafoam, a can of Lucas, is that going to? No, that is not going to fix this boat. We have a mechanical problem here. Okay, this is why this is my first test. There's nothing I can hang on that engine going to fix that until I fix this problem first. Okay, so let's identify our intake poles. Now I can do it the old school way without the piston position chart, because remember what I told you. Number 1's intake pole is 360 degrees from the spark event. So my green shaded area here is number 1's intake pole. All right. So I get these poles, I label them. So here's my poles, 1, 8, 4, 3, 6, 5, 7, 2. So I look at this and I go, okay, 4's pole's really good. 3's is okay. 7's is really good, right? These are somewhat, it kind of drops here, but 8's the guy that sticks out, right? 8 doesn't have much of a pull at all, okay? And you can see the pressure kind of goes up here a little bit, right? So he's the guy that my eyes are attracted to. I'm really attracted to number 8. So I'm thinking, what could be going on, right? So I asked myself, hey, Chris, cylinder 7's got to be our focus here, right? Number 8 intake pole is weak. 5 and 6 poles appear weak too. Number 4 is the deepest. No idea why, right, at this point. But you know what? I got to remember something. Stable cranking speed is my guy. Okay, we don't exactly have the best stable cranking speed here because we got a cylinder down. But I'm going to go ahead and use this piston position chart, and we're going to deploy this thing. All right. And you know where I'm getting it from. And I deploy it. And I jump in here and I want to look and see what's going on in this section. So I put these arrows in here to kind of reiterate these pulls. Okay. And I can basically tell here that I don't have much of a pull on cylinder 8's intake pull. Now I'm going to tell you right now, there ain't nothing wrong with cylinder 8. Okay, but his pull, his vacuum pull is being impacted here by something. Okay, so I go back and say, all right, Chris, it's cylinder 7. He's my guy. What could be going on in cylinder number 7 that could impact number 8's pull? That's what I'm after here, right? This is what I want to know. It's got my curiosity level peaked. I look, and I'm looking at this, and I'm going, cylinder 7's coming up on compression stroke, right? This is where cylinder 7 starts, or it kind of ends its compression stroke. He starts it here, but he kind of ends it here. So I'm thinking to myself, hey, wait a minute. If I got a leaky intake valve, wouldn't that affect on cylinder number 7? Wouldn't that put a little bit of pressure in the intake manifold, depending on the size of the leak? Yeah, you know, in the marine world, two-lipped intake valves are kind of common. For you guys doing a lot of marine work, it's not uncommon to have two-lipped intake valves in a Chevy V8. You know, it happens all the time. So I'm thinking, because let's go back to number 7's intake pull. And number 7's intake pull actually is one of the deepest pulls. Well, if I got a leaky intake valve, wouldn't I have more of a pull too, right? Quite possible, right? It's definitely not an exhaust valve, I wouldn't think, because cylinder 7's intake pull would be impacted, right? That's probably one of the best other than this one. And I'm going to get to that here in a second. So, excuse me, I do want to get to that. This pull here, remember right here, there's no compression. So didn't the crankshaft speed pick up when I had no compression? You know, that well, when the crankshaft speed picks up, doesn't the piston go down a little bit quicker? Won't he pull more air into the cylinder? So I could have a deeper pull. So that's why number 8's pull, right, is a little deeper. That's what I believe. So I asked myself, hey, Chris, what's going on in cylinder 7 that's affecting number 8's pull? So I say, hey, Chris, there's a loss of vacuum or an increase in pressure in the intake manifold just before number 7 fires, right? I have a loss of pressure, a loss of vacuum or an increase in pressure right here. So I go back. I really start hitting this home. I'm like, you know what? That is the compression stroke on cylinder number 7. It's the end, right? That piston, it's building compression. The piston's going up in the bore, right? That's when that slightly leaky intake valve could show up, right? Right here. So you know what? Let's do a little theory again, right? I got this little animation. Just pretend that this intake valve has got a leak, okay? Obviously it's opening, but let's say it's got a leak. Isn't that going to put pressure back into the intake manifold, right? He's going to put a little bit of pressure in here. My transducer is connected to the intake manifold. He can see that pressure. My old school Sears or rubbish vacuum gauge can't do that. I'd probably have a little bit of a quivery, but I don't know who the quivery is coming from. This is why I don't like to use an old school vacuum gauge, right? Great tool for its time, but this pressure transducer with a firing event, I can line this up. I can line this up with the other events, and I can make a determination on what could be wrong in a specific cylinder. Piston's heading up, that leak is bleeding into the intake. That's what I believe the problem is. This is why I tell my buddy, hey, I said, I think you got a leaky intake valve, cylinder 7. I said, we got some other sealing issues too that aren't exactly kosher, but I'm not even going to go through that. Number 7's our guy. You know, I believe it's time to pull the heads. Okay. And long story short, you know, the seller was trying to sell the boat. You know, he ended up making the concession and ended up selling the boat to my friend. I ended up fixing it for my friend. Okay. And everything was saved, right? The customer got to, the buyer got to buy the boat. The seller was happy. He got the boat out of his hair. He didn't have a blown motor, but we were able to tell this without spending any money. Okay. And here's the freaking money shot. We take the head off, and right here, you can see this is number 7. Okay. You can see that valve is kind of sucked up into the head a little bit. Okay. Doesn't have a hole in it, but it's definitely tulip and it's definitely leaking. And then I look in here after I clean the heads up. This is a video. I'm not going to play it because the sound is not going to come through. But basically, a long story short, I've got some pounding going on in some exhaust seats and other areas. You know, this boat was overpropped, it turned out, and it wasn't running top RPM, and that's what killed these valves and made it beat the absolute living crap out of these valve seats and stuff. Because you can actually see that exhaust seat there is pretty wide, okay? So again, I didn't go over the rest of the seats with this. Number one's my guy. That was enough information for me to make a determination, okay, on this. And when I put it back together, since I did this job myself, here is my post-repair capture. I crank it over, and would you agree that I have beautiful intake pulls here? 1, 2, 3, 4, 5, 6, 7, 8, repeat, okay? Beautiful starter motor current. This is what I expect. I never even took a spark plug out of this motor to figure out this issue. Now, I've got some experience in this. You know, like I said, I don't expect anybody to down one out of the gate here, but I'm sure you'd agree that this is pretty interesting technology and interesting techniques on how to go after something like this, a mechanical problem, and know that, hey, it's cylinder 7, it's the intake valve, and, you know, go ahead and let's buy this boat, right? And that's how this basically worked out. And this is how it was before, right? This is before, that's after. Nice, beautiful pulls. We did the diag really quick. Guy got to keep the boat. He ran all this past season, went and got drunk a bunch of times, had a beautiful time with it, okay? Loved it, okay? And again, old school compression test would have told me low compression, but it wouldn't have told me what was leaking. I'd have to do a leak down. Who wants to drag an air tank to a boat, right? Most of these docks, there's no air. You're going to go to a gas station. You got to have a tank. This takes way too much time, way too much time. And you can get diagnostics for this, right? I went down there. We did this right in front of the salesman, everybody, right? And this deal was struck right then and there, that quickly. I'm moving on. If there's any questions, let me know. But let's talk about crankcase pressure diagnostics with this tool, okay? And what I got coming up here is I'm going to use this crankcase, I'm going to use this pressure transducer, and I'm going to put it in an oil fill cap, all right? And I'm going to figure out if I can, I'm going to determine if I've got excessive crankcase pressure on a single cylinder or cylinders, right? And let's enter in our troubled vehicle, all right? It happens to be an 08 F450 6.4 Power Stroke, right? Another ATM machine for you diesel guys. And the issue here is cylinder 7 is setting a misfire code and the engine runs rough. It has a rough idle. Now, to do a compression test on this, right, I can do a relative compression test with the Ford factory scanner, which we did do, and it did come up low. But I don't necessarily know what the leak is, all right? And this thing wasn't huffing and puffing a lot of smoke out of that breather. But here's what I want to know. You see, I took a smoke machine funnel and I jammed it into the oil fill on this 6.4. And you see, I've got the star of my show right here, the WPS 500 transducer with a plug boot jammed into a nipple into this hose, and I got my scope. What I'm going to do is I'm going to trigger off a fuel injector, okay? And this is international, all right? And for you international guys, you know, they're a little politely weird, right? Number 1 cylinder's on the right bank, all right? Just so you know. And I'm going to trigger off an injector. And here's a wiring diagram. And I'm going to go ahead and I'm going to trigger off number 1 injector. These are piezo injectors. They're 2 wires. I'm just going to jump on the negative wire here, that black wire. I'm going to back probe it. And that way I can see when this injector fires. And I'm going to see if there's a correlation between this injector firing event and crankcase pressure. I roll this thing over. It starts. Boom. I run it for a grand total of 5 seconds. That's all I need. And I see something I don't like, right? I fire this thing up. I hit the space bar. I shut the scope down. I shut it off. I analyze, all right? The blue is my number 1 injector trigger voltage signal. And red is my crankcase pressure, okay? And would you agree, it looks like I've got a sharp increase in crankcase pressure that repeats. So we're going to zoom in here. I zoom in, this is number 1, right? I definitely see a repeating issue here, right? I mean, this is number 1, this is number 1, this is number 1, this is number 1. Would you agree that there's a rise in pressure, and it looks the same? Now, I don't know what's going on, maybe quite just yet, but I grab my red horizontal cursor and I look, and it's about half a PSI. So it's not a lot of pressure, but it's a half a PSI. Okay, so it's not like we got 10 pounds of pressure in there, which usually crankcase pressure is kind of light anyway, right? But whatever's going on here repeats. So let's zoom in to 1/720 cycle, right? This is injector number 1 firing. This is injector number 1 firing, okay? And then I've got this rise in pressure, and then it kind of goes out. And then I got a rise in pressure again, all right? So I'm gonna use my phase rulers, okay? I dump 8 partitions in, same thing, all right? And I see that the pressure starts to build right here. So I put my firing order in, right? I don't expect anyone to remember this, right? But it's 1, 2, 7, 3, 4, 5, 6, 8, 1, right? Well, remember number 7 sets a misfire code, right? This is when number 7 cylinder fires. Would you agree that the pressure buildup is right about where number 7 cylinder fires, and then it falls off the face of the earth, and this repeats? I got a crankcase leak. This thing's got a cracked piston, right? It's chipped up. It's all ready to go, right? Right here tells me that, hey, cylinder 7, it's a crankcase leak, right? We didn't take a glow plug out. I didn't take a valve. We didn't do any of that, right? This is maybe 5 minutes of screwing around, right? It's going to take me longer to get my computer out than it is to do this test. And if you think I'm kidding around, let's use the piston position chart, right? I pop in the piston position chart. Guess where number 7's on compression? Right here. And about halfway through its compression stroke, there's a nice sharp rise in pressure in the crankcase. Dunzo. Finito, right? We're done. We told the shop, and this is actually a local construction company here. They got their own mechanics. They just brought it in here for a diagnosis. But I said, hey, dude, you got a piston problem. You have a piston to cylinder wall issue here. A leaky valve is not going to put pressure in the crankcase. I'm sure you would agree with that. Okay, and this is something quick that I can do. Right? It took no time. That's why I love this tool. That's why I love these techniques. I've got plenty more case studies. I'm only doing this one for that. I've definitely got gas engines, but I want to show you. I want to throw a diesel in there because I know diesels are a hot topic, right? You know, they're rebuilt a lot. They're chipped up a lot, right? These guys, they got the freaking big exhaust. They got the 5-inch sewer pipe exhaust through the bed. They cut holes in. They beat the absolute crap out of them. They got propane injection. These things get whooped on, okay? And if you're doing engine work for these people, right, and these guys come back, you know, and they give you this, right, you can say, hey, you know, it's a crankcase leak. This is what I like about this. Okay, good. This is good stuff. Right there, my compression stroke. All right, I showed it to you in a crankcase. I showed it to you in an intake manifold. The last thing I want to show you here before we get into a bunch of case studies is I'm going to show you this transducer in a cylinder, and I'm going to show you what we can do inside of a cylinder. All right. Same basic premise. We're going to do a cranking compression test. We're going to do a running compression test. All right. Running compression test is an old school test that nobody hardly does anymore. And with an old school Sears and Rubbish compression tester with a Schrader valve, there's 2 schools of thought, right? Leave the Schrader in, rip the Schrader out. With this, we don't worry. There is no Schrader. All right. And this is why I use this tool to do my diagnostics. All right. If I want to know where dead nuts ignition timing is, I use this guy, okay? I'll show you how I do that. And one thing I'm going to mention is when we look at we look at an in-cylinder cranking compression, I don't care about the first peak. The rest of the peaks I do care about, and I'll talk about that here in a second. And if I've got compression peaks that have excessive variation, kind of looks like a saw, you know, a hacksaw blade, then I can bet money that I have an upper end sealing issue, right? I got valve issues, the seats are beat out of it, you know, something like that, right? Because the valves aren't sealing the same every time. Running compression, when I get to that, same thing. I'm actually gonna put less time on the screen, 2 milliseconds per division. I know that may sound like jargon to some of you. I'm gonna disable the fuel to that cylinder if I can, if it's easy. If it's a bunch of work and I can't get to the injector, I'll be honest with you, I don't disable it. I'm not a huge fan of fuel just spraying into a cylinder, but hey, I'm a diagnostician. The diagnosis got to get done. If I got fuel spraying in there for 5 seconds, who cares? Okay, because honestly, I don't have to run this engine longer than 5 seconds. Okay, most generally. I can find exhaust path restrictions super easy. Okay, a good spec of running compression is 1/2 to 1/3. And the question always comes up is, Chris, why is running compression lower than cranking compression? Well, the answer is simple, right? When an engine is running, right, there's less time for air to fill in the cylinder. When the engine's cranking and going slow and the piston's going up and down, right, I've got more time to get air in the cylinder. But when that thing is idling and it's doing this, there's less time to get air in. That's why running compression is lower, okay? A couple things I can do that I really like. I can identify exhaust valve opening, okay? It ain't degree wheel accurate, okay, but it's close, okay? Like I said at Epic, right? I'm not Robert Yates. I'm not, I'm not Rick Hendrick, okay? We're not going for dead nuts accuracy, but it can give me an idea where the exhaust valve opened and where the intake valve closed, okay? And that's why I say, right, this does not replace a degree wheel. I don't want you to think, well, shit, I'm not going to do any more degreeing. No, okay? This is, as a diagnostician point of view, I want to know, is that cam in or out, okay? And I'm going to show you with some cam specs on how we can determine this on a case study coming up, all right? So, because guess what? When we put an engine together, right, and it doesn't start maybe, okay, or I got problems, I may want to know where that cam is, or if it was ground right, if it was put in wrong, if a keyway sheared. I tell this all the time, right? If I have dots on timing gears, right, or lines, or whatever you want to call them, or special tools that hold stuff together, those tools or those dots are only there for our eyes. Just because dots line up and marks line up does not mean that engine is in time. Those dots are immaterial sometimes, okay? I know you guys out there probably worked on 5.4s with those pins shear, or the reluctor moves, okay, and the cam is still dead nuts in, sometimes very difficult to diagnose, right? So I can identify exhaust valve opening and I can identify intake valve closing. Those are the two events that I can ID with pretty good certainty, okay? I can't identify exhaust valve closing and intake valve opening because that's on overlap. And as you're well aware, both valves are open at the same time and overlap. So the only time I can identify those is when I have issues, okay? And that's why I say the rest of the valve events are cloudy unless I got problems. This happens to be a 4.5 liter Merc Cruiser, okay? This engine here is Mercury Marine's own engine. It's based off of 4.3. It's very similar. It's their own block, their own heads. But this thing's got 186 PSI, right? And I got this line right here. I just put this transducer, right? And here's what this hose looks like. I got a compression hose right here. And one thing with Pico on the newer hoses, they have all kinds of different adapters you can buy for all sorts of edges, 12 millimeter, Triton, 10 millimeter, 14, 18, they've pretty much got an adapter. And this has got to be a decent hose, okay? We're not doing this with no Gates push lock or anything like that, right? Because we're dealing with compression here. And if you run the engine for any extended period of time, this hose will get warm, right? Because you got compression coming up through it, all right? So these are good hoses. I get them right from Pico. I just want to make that mention because, again, I want a stiff hose, right? I mean, I don't want a nylon braid hose from a Sears and Rubbish compression gauge. I don't want that thing really expanding because that could dampen my reading, right? I need something that's stiff and I need something that can give me a good, repeatable reading that I can analyze. I'm at 186. Remember what I said earlier? I don't care about the first one because I have no blanking clue where the piston was in the bore when the engine got shut off, right? When I started cranking this thing, hell, that piston could have been all the way up in TDC, could have been on its intake stroke. I got no blanking clue where that's at. But everybody else better look like this, right? My old school compression gauge, right? What are you guys? 3 pumps, five pumps, right? 3 pump and dump, as I like to say, right? So you sit there and you pump it, and your compression gauge, it traps all that stuff, right? This thing doesn't trap anything, right? I mean, I'm looking at each time that look at that thing. I mean, in what do I got here? 12 seconds of cranking, right? I mean, I got a bunch of hits, right? So I can evaluate those valves really, really good, right? If I had some intermittent sealing problem like carbon on the valves, like on a GDI engine, this is a great way to figure this out, right? I got misfires kind of counting on cylinder 5 or something like that. Maybe a cranking vacuum test that didn't show up. I'm going to jam this transducer in there and I'm going to disable it. I want to crank this thing over 10, 15 seconds, right? Because again, cranking, that valve is closed longer. I have more of a time or more of a chance to evaluate it cranking than I do running. Okay, so this is what known good looks like. This looks really, really good. Then I fire this engine up, right? It's sitting there running. I run it for maybe a grand total of what, 16 seconds, something like that. I shut it off. And on a running compression test, I am not using a horizontal line, right? And the reason is because the RPM, right? I mean, number one, this engine's a V6. It's only running on 5 cylinders with my transducer in one hole. So the idle is going to be a little erratic. So I'm not going to have the same compression peaks here on a running compression. Cranking, I'm all about it. Running, I'm not. And as you can see here, I got 133 pounds of running compression. Let's zoom in, okay? And there's a few things I want to make a point here. We call these our compression towers, compression peaks, right? This is where the piston went all the way up in the bore. It was all the way up in the bore, and then the piston got drug all the way down, right? This point right here is where the exhaust valve opened, all right? This is my exhaust stroke. Should be close to 0 PSI. If I got pressure here, I got some kind of restriction, the exhaust valve didn't open, something's going on. This is the valve overlap area, 360 degrees. This is my intake stroke. Right here is where the intake valve closed and the piston went back up the bore. So between here and here is 720 degrees. A couple other items of note. We call this the expansion pocket, okay, because the piston got drugged down the cylinder. The expansion pocket, remember both valves should be closed, right? Normally the spark plug would have fired and an explosion would have pushed the piston down on its bore. But since the spark plug ain't in there, my transducer is, there's no combustion. Piston got drugged down the bore and I got my peak vacuum right here, okay? My intake stroke should be the same vacuum, which is right here. And I like to draw a line there because the term I learned is very simple. The pressure I start with, which is right here, is the pressure I end with, all right? So the pressure I start with, the pressure I end with, all right, should be the same. I got a leaky exhaust valve, something like that. This is elevated over here on the intake stroke, right? Because aren't I going to have a little bit of pressure coming into the cylinder potentially? Okay, not going to build enough. This also could be affected too a little bit, depending on the leak, okay? But this is what I'm always looking for. So I bring my phase rulers in, right? I go right here to 0. I line that up with one tower. I go over here and I go right here to the second tower. Bam. I select 8 partitions. I know I'm in one cylinder, but I like looking at every 90 degrees. All right. That's why I come over here and say 8 partitions and I line it up. And now I've got inside the cylinder, I know exactly where that piston's at, right? 90 degrees, it's halfway down. 180, it's all the way down. 270, it's half up. 360, it's all the way up. 450, it's half down, so on and so forth, right? 540 is bottom dead center. You get the idea here, right? So I know where this piston is in the bore, right? Pretty accurately. And here it kind of just hits on what I just told you, right? Right here is my expansion stroke, my vacuum pocket, okay? This is my exhaust stroke. This is my intake stroke, right? I'm looking at my old school compression gauge can't tell me this. This is one of the reasons why I use a pressure transducer. Ever since I've learned how to use this about 15 years ago, I've never looked back, right? I keep practicing my skills on this stuff because there's so many things I can do here, okay? And like I said, I built -6, little over 6 PSI of pressure, right? Which if I multiply that by 2, means I've got 13.5 inches of mercury, which that's pretty decent vacuum inside of a cylinder, right? For this engine specifically. Let's identify EVO, exhaust valve opening. I'm going to put my cursor right at the 180 mark, right? 180 is bottom dead center. And I'm going to take my other vertical cursor and I'm going to line it up right to where the pressure just starts to increase. That is precisely the moment the exhaust valve opened, right? Because think about this. This thing's in a vacuum. The exhaust valve typically opens on most everything that I'm working on, all right, 30 to 60 degrees before bottom dead center. That's when I expect an exhaust valve to open on the engines that I'm working on. Now, for you guys out there, you're building specific race engine or specific applications. If you've got the cam card in that, this is where I want you to practice and do this stuff on the dyno or whatever. You can kind of see where your stuff is. You're building a specific dirt motor, you're building a supercharge or whatever you're doing. You know, you need to learn your environment and learn your engines, okay? Then you can go in there and say, you know what, something's up. I think that cam's wasted, or that valve's too loose, or the push rod's bent, or whatever, okay? But I measured right here, I'm about 42 degrees, 41.94 to be exact, but that's within my 30 to 60 degree before bottom dead center window. I jump over to the intake valve closing, right? Same thing. I put a cursor at the 540 mark, okay? The 540, the piston's all the way down. Typically, in the stuff I'm working on, old school GM, you know, stuff like that, I expect the intake valve to close 30 to 60 degrees after bottom dead center, okay? And that's exactly where I'm at. I'm right in the, you know, kind of in the middle of my spec, right? 44 degrees after. I line up that cursor right where that pressure starts to increase. That's precisely when the intake valve closed. Because think about it. When does compression build in a cylinder? When the intake valve closes. Yes, the piston does have to go up on the bore, but you know what? That intake valve is held open in perfect conditions, you know, or the correct conditions. The intake valve is open, right, for just a little bit as the piston goes up, then the intake valve closes. As soon as you see that pressure start to go up, that's when I know the intake valve closed. Simple as that, right? And 30 to 60 degrees is very similar. I should have put that in. I stole this slide out of something else. I apologize. But EVO is 30 to 60 degrees before bottom dead center. Intake valve closing is 30 to 60 degrees after bottom dead center on the engines that I see, okay, for the stuff I'm dealing with, right? Passenger car, light truck, marine, that kind of stuff, all right? You got to know your environment. I stole this from Pico. Thanks, Pico. This they have on their website, picoauto.com, and I put this in here. You can have it in your handout. Kind of explains everything I just did. You know, it talks about the expansion pocket, the exhaust stroke, the intake pocket, and our compression peaks. It's in bar, which is okay. We can convert bar to PSI. Now, with that said, I've got some case studies that I'd like to tackle. All right, I gave you a really, really quick crash course. I know I only got 2 hours to do this, but I'm trying to put enough information in here to kind of get you guys thinking. And what I got here is I got a 2018 Silverado with a 5.3 LT engine, right? It's got 168 on the clock, and a couple things are going on, right? It's for a local contractor here that does some landscaping, right? It's got a squeaking noise coming from the engine, all right? Now, you already know it's an LS engine. You probably already know the camshaft's probably wasted, right? You got squeaking noises. You know, it's very, very common. And that's why I picked this case study, because I want to show you how I can figure out who, what valve, what lobe without any disassembly, right? That's my goal here. So here's the rundown. It doesn't have any codes, all right? Their complaint is like a fish bite miss at idle, okay? And there's an intermittent squeak noise. And he says, Chris, I can't tell where it's coming from. Now, I put this GMTSB in your handout. I am not going to go through it, okay? It's multiple pages. It covers basically every LS and LT engine, right? 02 to 23. So there's a problem here. I'm sure you would agree with me. And they say, hey, Chris, you know, misfire, chirp, squeak, squeal, tick, check money lights on, trade-in lights on, whatever you want to call it. Okay, I got it. All right. But they tell me, they go on this bulletin, they say, hey, Chris, you could have a worn cam lobe. You could have a sticking valve. You could have valve leakage. You could have a broken valve spring. You could have a collapsed AFM lifter. I agree, right? But how do I know, right? How do I know? I don't disagree. It could be all that stuff. But they basically go on to tell you that, you know, they want you to take valve covers off and this and that. We ain't going to do any of that. I'm using an Altel scanner here, not my GM, but I noticed a couple clues. okay? Now remember, there's no codes. So one of the first things I like to do is look at misfire history, okay? In misfire history, I've got 171 misfires on cylinder 5. Now these guys got their own shop, this landscaping company. So I don't know if their mechanic blew the codes out before it came to me. I don't know. I didn't pay attention. I actually wasn't the guy who actually diagnosed this. One of our technicians did. Okay. I just assisted him on it. That's all I did. But the first thing I noticed is 171 misfires on 5. I'm like, okay, you know, not a ton, but I'll put that in the back of my mind. You know where I'm going with this. Let's do a relative compression test, right? Along with cranking vacuum, right? It's what I've been talking about for an hour and a half. Let's do it, right? So I disable the fuel on this thing. I roll this 5.3 L83 RPO code over. This is what I got. Let's zoom in. Ooh. I got something going on here in the vacuums. I mean, naked eye, my blue is my starter motor current, by the way, and green is my cranking vacuum. And I got something that kind of repeats and then it kind of goes away. It's not as obvious maybe as what I showed you earlier, right? But let's just focus on one thing at a time here. Relative compression. Here's my starter motor current, right? I bring in my cursors. I got 70 amps peak to peak. Is that over my 35 amp minimum for a gasoline engine? Yes. And would you agree that looks like everybody is touching my horizontal upper line there, right? So you know what that tells me? I don't have a leak in a cylinder. I ain't got no leaks, okay? So guess what my compression gauge would have told me, right? Nothing. I would have put a compression gauge in probably every cylinder and they would all been 200 some PSI, right? So a compression gauge was not going to tell me what was wrong with this motor, right? I look up the firing order. Let's say it's my first day on the job, right? 187265543, typical LSLT firing order, correct? And this baby's got 11-to-1 compression, right? This is a GDI motor, you know, 11-to-1. This ain't an old school 350 Chevy with 120, 130 PSI, agreed? That's not the case here, right? This is 11-to-1. This is serious compression, all right, on pump gas. So I blow this up just for me and I identify my cylinders here. I don't see anything here that tells me I should chase, okay? I've got the same compression starter motor current peaks everywhere. Nothing going on here. I mean, you could say maybe 3 is a little less or whatever, but nothing here that I can say, yep. Okay. But remember, number 5, I'm counting misfires. And look at number 5. Doesn't he look pretty good here as far as starter motor current? Hey, how about my ignition timing, right? I don't have to put cursors in, but would you agree that my spark line is at or right about the peak of the starter motor current, right? Don't most engines fire at or before TDC, right? 10 degrees, 5 degrees, 12 degrees, 0 degrees, right? So what's that tell me? It tells me my reluctant wheel, my crankshaft hasn't moved, right? You want to pull the pan and figure out if the reluctant wheel, this is why this is one of my first tests, right? I know that spark is happening really close to TDC, right? I'm a big fan. Let's deal with this cranking vacuum. This is all over the place, right? I've got all kinds of pressure peaks here. I got maybe some deeper vacuum here. Let's pick one of these quote unquote bad ones, right? That's what draws my eyes. My eyes are drawn right here. Looks like I'm getting pressure, right? Remember I said earlier, the deepest vacuum is at the bottom of the pattern. Well, whatever looks like happened, looks like it just went up freaking Mount Everest, right? Just a complete rise in pressure. Bam. And then I come over here, 8 poles later, boom, something just took off. I don't know, right? So I see a slight loss of, I move down, right, to 2 spins of the crank later, and I see a little bit, not like this, but I see a little bit of a loss of pressure, but it's not the same, okay? And the reason I use this case study is because not everything is going to be a pretty picture where it's bam to bam to bam, right? But I can still do the analysis. I pick out my my cranking vacuum. I want to know the vacuum poles, right? 1's got a pole, 8's got a pole, 7's got a pole, 5's got a pole, 6 has got a pole. Ooh, 5. Ooh, not much of a pole, right? There's definitely some kind of pulse, pressure pulse in number 5's intake pole. And then I start to pull vacuum back down and then bam. And this thing repeats. Number 5's intake pole is impacted here, okay? And that is a huge clue. That is a huge clue, all right? So you know where I'm going. I'm grabbing my piston position chart, right? I bring my piston position chart in, okay? I expand it out over number 1 to number 1, right? I got it expanded out, that's 720 degrees. I looky right here, right? I'm looking, and number 5's intake stroke is right here. And I'll go back where I don't have this red box in here. Would you agree that at approximately the beginning of the intake stroke is where this rise in pressure in the intake manifold happens? Isn't this an intake manifold? This thing's not supercharged, right? This is not a 6.2 LSA. It's not some go fast caddy. This is just a regular wore out Chevy 1500, right? There should be no pressure in the intake manifold. So this is where I'm saying this is something's up here, right? And I have to make this comment too. This is a an idea, okay, or a rough idea where the intake valve opens. Just because you line up this piston position chart right here, for instance, that does not mean that that intake valve specifically opened right then, okay? It tells me I'm in the neighborhood. Again, this is not a degree wheel, but this gives me the visual for my eyes, which is what I need to diagnose this stuff. I need a visual, and I need a visual to see this, right? And all I know right now is pretty much when the intake valve opened on number 5, I had a boost of pressure or a burst of pressure inside the intake manifold. That's all I know, okay? That's all I know at this point. So I got to ask myself a question. I got a leaky exhaust valve. We think the cam's bad, right? I mean, LS, I mean, if you haven't had a cam go bad on an LS, you got slighted, right? It's not if, it's when. So my point here is let's think about something, right? I've got valve overlap, right? And let's say the exhaust valve didn't open. And typically, when you have a bad camshaft, all right, or a loose rocker arm or a bent push rod, two things are pretty constant, right? Number one, the valve opens too late. And number two, it closes too early. Most cam lobes don't wipe completely off and don't open at all, like an AFM lifter failure, right? Most time the cam, it opens late, and it opens like real tiny amount, right? Depending on how long the people have been driving it. Okay, generally speaking. So let's say hypothetically, let's say the exhaust valve closed way too damn early. Well, if the intake valve opened, remember we have valve overlap, right? If the intake valve opened and the exhaust valve closed too early, wouldn't I have a little bit of pressure left over in that cylinder, right? The exhaust valve should still be open, right? Because aren't the intake and exhaust valves supposed to be open at the same time for a little bit? Don't we call that valve overlap, right? So if that piston's going up and that exhaust valve closed too early because the camshaft lobe is wasted on number 5's exhaust valve, isn't that going to trap a little bit of pressure in the cylinder right here? And then when the intake valve opens, I think so. I think that's a very damn good possibility. I got a little synopsis here. I'm not reading it to you, but long story short, I see that the pressure seems to happen at valve overlap, right? As soon as that intake valve seems to open, and it has the look of a worn exhaust cam lobe on cylinder, right? On specifically cylinder 5. You know how I'm going to tell us 100%? I think I got 100% now. I'm going to go in cylinder on cylinder 5. So first thing I'm going to do is I'm going to run to all data, and I want to know what compression is supposed to be, right? So I go there and they say, hey, Chris, anything over 100 and everybody within 70% of each other. I'll be honest with you, I only went in one cylinder, but with relative compression, I didn't see a problem. And if I would have followed GM spec here, I wouldn't have found this, believe me. So our technician Johnny here, I got him pulling the spark plug out of cylinder 5, right? You see I got my piston position chart here. I said, Johnny, go ahead and yank that plug out. We're jamming the transducer in, okay? We jam the transducer in. Again, I don't care about number 1, could care less, because I have no blanking clue where the piston is. When I bring my horizontal cursor down, I got 206 PSI. Hey, 11-to-1 motor, that's actually right. 11-to-1 L83 GM53, I'm excited. I'm excited. But there's something I see here I don't like. And that's this. You see these little things look like thorns, like a rose bush right down here. And I've looked at a lot of relative compressions on these GM engines, or excuse me, in-cylinder compression. I don't see that, right? So I go in here and I go, hey, what the hell is this, right? What is this? Huh, I don't know, right? So I go in here, I look at this, right about the 360 mark, right at the valve overlap, right? Almost kind of like where the intake valve opens, right? Let me throw some numbers at you. So I think the exhaust valve might be the key here, right? So let's do my EVO, right? I measure my EVO, it's 34 degrees before bottom dead center. Remember Chris's spec, pretty much 30 to 60 on stuff I'm working on. This thing is really approaching that 30-degree number. Now I will tell you, there are other engines that are way past 30 degrees, closer to TDC. I get that, okay, or bottom dead center. But for this engine, like I say, I've got some experience on these, and we're approaching way too late. And one thing about scoping, if I have anything to the right of where it's supposed to be, anything to the right is happening later, or it's retarded, right? My friend John Thornton calls it the double R rule, right? If it's anything's to the right, it's retarded. This EVO is late, right? If I got a worn cam lobe, bent push rod, rocker arms trash, you name it, you can pretend that valve's going to open too late, right? And it's going to close too early. If that valve closed too early, couldn't that cylinder build a little bit of compression at the end of its exhaust stroke too, right? Yeah, I think so, right? And this is kind of where I'm tying this all in, right? Cranking Vacuum told me this. I go in cylinder, I see this. Now I really got solid information. Now I'm like, yeah, baby, we got this thing nailed. Fire it up and I look and I see a big pulse right here, right? I'm looking at that. It's a lot worse running, right? And I normally like to evaluate these engines running, not cranking, right? I fire this engine up running. My EVO is now, it's below my 30 number running. It's at 23, right? That's no bueno, man. In any language, no good, okay? That is way too damn late, all right? And I got this pressure pulse here, right? And this is what I said, right? You got a bad cam, it's going to open too, the cam lobe is going to open too late, it's going to close too early. That EVO is way too late at 23 degrees. It should be way more advanced than that, okay? And let's say it's my first day on the job. Let's say I don't know. Let me check my next door neighbor. I can always check another cylinder if I wasn't sure. Chances are I have multiple bad cam lobes. That's some flat tappet thing, right? But I put this in here. You guys are mostly engine builders. You get it, right? When a cam lobe is worn, okay, it's going to close too early and open, it's going to open too late, close too early, okay? I'm going to have a trajectory like this, okay, just to give you a visual. Let's go on number one cylinder. I did pull number one's plug out. I rolled it over. I had exactly the same compression, 206. But guess what? I don't see any rolls. I don't see any thorn bushes down here, not cranking, right? I fire this thing up. I do running compression. I check my EVO. It's 48 degrees, right? Would you say that's a lot better than 23? It's a huge improvement, huge. And guess what? At the valve overlap, I don't have a big rosebush thorn here. And if I go back, actually, I didn't put a cursor here. This is 15 PSI right here. If I would have put a cursor here, I'm over 15 PSI. My compression gauge can't see that, old school, right? My transducer could, okay? That's a clue. That's a clue to what's going on here, okay? So back to my case study here, right? I'm at 48. I know 100% that this thing has a worn exhaust cam lobe on cylinder 5. We did this diag in 15 minutes. I ain't bragging, okay? But we didn't take a valve cover off. I took number one plug out just to prove a point on this engine, right? And turns out the customer did not want to fix it, right? He's like, Chris, I'm not putting a cam, I'm not putting a motor, I'm not rebuilding it. He goes, it's a wore out old plow truck. I'm 86 in it. It's file 13, goodbye. But you know what? We did our customer a favor. We didn't take all this crap apart to tell him something that he wasn't going to fix, right? He paid our 1 hour diagnostic fee. Our labor rate here is 150 bucks an hour. I'm not afraid to share that with you. And we got $150 to spend 15 minutes on this thing, and we wasted zero on this. In my opinion, there was no better way to diagnose that at all. Next one, I got a 2002 Nissan Xterra, okay? It's a 3.3 V6 supercharged. We put a new reman motor in. I ain't telling you where it came from, okay? It's a very popular place. They do good work. You know, anybody can have problems, okay? But we put this motor in and we got issues, all right? So I'm gonna cut right to the chase. I roll this thing over. This is cranking vacuum, all right? This thing is ticking and it idles very, very rough. And this is my cranking vacuum pattern. This is number one cylinder. You guys have listened to me now for almost 2 hours, right? Would you agree that I've got 3 pulls that are deeper than the other 3 pulls? Let's count. 1, 2, 3, 4, 5, 6. This is a V6 engine. It's a single overhead cam engine. You know what I know right here? We've got one side of this engine that is breathing much better than the other side, almost identical. Pretty interesting. How many spark plugs are going to fix this? How many mass air meters are going to fix this? How many cans of Lucas fuel treatment in the gas tank? You see where I'm going with this? We check this thing out. It didn't sound right. We instantly go to cranking vacuum relative compression, and this is what I see. We have a mechanical concern, period. Okay, now I want to know what's going on, right? So I blow this up, 720 degrees, right? I got my 3 deep pulls. I got my 3 not so deep pulls, but I want to ID them. Okay, I use my phase rulers, okay? And I'm gonna select 6 partitions because I have a 6-cylinder engine here, right? So I should have 1, 2, 3, 4, 5, 6. And look, I use my horizontal cursors, and I'm sure you agree with me that I have 3 pulls that exactly meet the bottom line, and I have 3 pulls that pretty much meet the top line. This engine is the same cubic inch, I sure as hell hope, on both sides, right? Why would one side of the engine be breathing better than the other? Like I said, there's no spark plugs, no fuel injectors, no nothing's gonna fix it. This is a mechanical problem here. Mechanical all day long. But these deep pulls are what I'm attracted to, right? And I just say, I don't expect anybody to be a Nissan tech here. So this is the engine. Bank 1 is on the passenger side. That's the right bank. Okay, 135246. All right, that's where I'm at. This is number 1 spark plug wire, right? Where's number 1's intake pull? 360 degrees, right? So I'm 360 right here, so that I can put cylinder 1, 2, 3, 4, 5, 6. So look at this. And my firing order is 1, 2, 3, 4, 5, 6, right? So guess what? Bank 1 is not breathing as good as bank 2, period. So I go to my compression check, right? I go to all data. I don't know about you. I'm not a kilopascal guy. I'm a PSI guy. But they basically say, I did the conversion for you. Hey, Chris, 128 PSI to 173. Okay, thanks. I mean, so I jam a transducer in cylinder number 1. I got 171. That's almost to the top of their spec. Huh. Hey, but look at this. I got a rose thorn bush down here at the bottom, right here at the overlap. You've already seen this, right? Something's up. Something's up. I got a thorny bush right here. That shouldn't be. That shouldn't be. Okay. Something's going on at the end of the exhaust stroke. I measure it. It's 11.5 psi down here. Whoa. Shouldn't have 11 psi. Is my compression gauge going to see that, right? Isn't that Schrader valve going to trap that? This is no way, right? Cylinder 2, cranking compression, right? This is the other bank, right? The suspected good bank. I got a $160, right? I had a $171. I got 10 psi more compression on bank 1 than I do bank 2, all right? But if I look at Nissan spec, I'm well within their spec, right? So one might go down the rabbit hole. And this is why with an old school compression gauge, you know, when you sit there and pump, you know, you may not have caught this. But cranking vacuum, Stevie Wonder could have caught it, okay? That's how obvious this is with cranking vacuum. I'll cut to the chase. They had the timing 1 tooth off, right? We put a mark here. It's supposed to be right there. and it was one tooth retarded. That exhaust valve closing at the wrong time, right? One tooth retarded. And turns out this engine had another issue. It had oil, it didn't have any oil pressure when it was hot, and there was oil leaking around the lifters. That's why it was clattering, which that also affects valve timing. I would have shown you in cylinder doing EVO and that, but they were all pathetic because the lifters were pumping down at idle because this engine only had like 4 psi of oil pressure when it was warmed up. We didn't even give this car back to the customer. We started up, it was instantly ticking. When it was cold, there was no ticking. It ran rough. We put the cam in time. The engine ran a lot better. The cranking vacuum was good, but I had that ticky at idle. And of course, when you have a lifter that's pumped down, isn't that similar to a worn cam lobe? Intake, the valves are going to close too early, open too late. So my EVOs and IVCs were all over the place. But long story short, we got a hold of the engine supplier. We told them what's wrong. I fished them this information. They kind of had a hard time believing it at first, because they wanted old school compression numbers. And I tried to tell them, look, it's not going to tell us what's wrong. And when we took the valve covers off, I used an oil pressure tank, and you can see the oil gushing from the lifter bores in this Nissan head. They actually sent us another set of heads. We put them on, everything was fine. So that's basically the end of this story. Let's do another Nissan. I got an 05 Nissan Frontier, 4-liter V6. You're thinking this is a Nissan class, right? Well, but here's what I want to show you. I want to show you another similar engine. It's a 4-liter. I'm going to show you a different take to this problem. Okay. And turns out I did this diag here at the shop here just this past summer. And long story short, vehicle was towed to us and it was really running like crap. Okay. Really running like crap. And bank 2 cylinders are all counting misfires. Okay. And when you have a bank-to-bank engine, I know this isn't really a drivability class, even though I'm kind of making it one, but you should always look at fuel trims. All right. That's one of the first things you should look at. And I know you're not Nissan techs, but Nissan uses what they call Alpha. Alpha Bank 1, Alpha Bank 2. That's the fuel trim correction. And if you're not a Nissan tech, you see one here is 121% and the other bank is 83%. And in layman's terms, in a perfect world, you want that around 100%. Okay. And when that's around 100%, that means I have very little fuel correction going on. But bank 1 is getting a bunch of fuel, 21% more, and bank 2 is getting fuel ripped out of it, right? 17%. And the key here that I want to show is this is a mass airflow engine. And when you, on a mass airflow engine, when you have a bank-to-bank trim imbalance like this, automatically means you have a cylinder breathing issue, or you have a bank-to-bank breathing issue. This thing can't breathe, okay? It can't breathe. And this is what I mean here. I put this in here. Anything over 100% means it's a positive correction. Anything under 100% is a negative correction. And I will tell you that the bank with the negative correction is the bank you chase 99% of the time. The bank that's negative is the bank you chase. All right. Because they're about 20%, right? I got almost a positive 20% correction on bank 1, and I have almost a positive, or excuse me, negative fuel correction on bank 2, right? This is a V6, it's a V engine, right? It should be, why would I have fuel trim that is exactly skewed almost the same number, right? It's not, it's a Nissan. You already went through this, right? Bank 1 is 135 on the right side. Bank 2 is 246 on the left, right? I see my fuel trim skew, and this is when I want to hit home. I've got this engine here. I got a mass airflow meter. I just want to hit something here to show you something else. All right. Let's pretend that the engine's idling, whatever speed it's idling at, and obviously the engine has the same breathing capability in every cylinder if everything is correct. If the exhaust can breathe, if the intake valves can, exhaust valves are working, all that stuff, air filters not restricted, blah, blah, blah. Everybody should be consuming the same grams per air. In this case, 6 grams of air per on this fake V8 engine, right? So 8 times 6, since it's a V8 engine, is 48 grams a second. Okay, so that's what the mass airflow would be seeing in this example, right? Because each cylinder is pulling 6 grams. Let's say I got problems. Maybe I got valve timing off, restricted exhaust, you name it, okay? Well, on a mass airflow equipped engine, I'm gonna have a fuel trim skew. Why? Well, The computer sees 40 grams of air at the same RPM, right? Because this side doesn't breathe well. In this example, bank 1, okay? So what happens is the computer divides that out, right? So it says, hey, wait a minute, you got an 8-cylinder engine. I'm going to divide 8 into 40, which means everybody is consuming 5 grams of air. Well, this thing's actually moving 6 grams of air because he's breathing good. Bank one that has the problem, he's got some kind of valve timing issue or exhaust restriction, and he's can't breathe as well for whatever reason. So that's why this bank is rich and that one is lean. Okay, that's how this works. Okay, so first clue when I look at this Nissan is I got a trim skew. Okay, that's clue number 1. All right, and I'm not, same thing. This just goes to show you that I explained the fuel correction because I want to get to something else here. So I got negative trims on bank 2 in this, my V6 case. Okay, the scanner had no cam timing codes. All 4 cams are monitored on this. So if I had cam timing problem, at least with the chain, you would think I would have codes there, right? So I'm thinking to myself, Chris, it's most likely not a cam timing problem, right? So let's do a relative compression cranking vacuum. That's what I'm hitting on, right? So I got a clue that tells me to do this with the scan tool, fuel trim skew, and let's do it. So I roll this Nissan over. It's cranking, and look what I got. Let me zoom in, right? First thing I notice is, looks like I've got higher compression and lower compression. You see high, low, high, low. Look at my cranking vacuum in the green. Would you agree that I don't have even 6 pulls here? And I happen to be on number 4 coil because number 1 coil is under the intake manifold, and I'm too lazy to go get it. So I'm going to grab number 4's coil because he's easy and he stares me in the face. So I blow this up a little bit more, a few 720 cycles here, right? I put red arrows on where the compression appears to be lower. The next one's higher, high, low, high, low, high, low. I don't know who anybody is yet, but I see a trend. I see a pattern here. Same thing with the cranking vacuum, right? I've got 3 pulls that are really good. I've got 3 that aren't so good, right? And then here's 720 degrees. And I'm looking at this. And I see something I don't like. I see a lot I don't like, but there's something that really picks out. Look at these intake pulls. Would you say that they've got some ruffles, ridges, I call them? You know, ruffles have ridges. Remember that commercial, potato chips? Would you say that 3 of these pulls have some kind of freaking saw blade effect to them that I don't have on the other one? What the hell is that, right? I mean, that's not normal. The pull is weaker and it's got some kind of ruffle. So I blow this up again, right? Not really smooth. The ones I've showed you so far look really smooth. This thing don't really look smooth, you know? So I'm looking at this going, I don't like it. I don't like it. I don't like it. Something's up. Something's up. I got low compression here. I got crappy pulls with some kind of rippling effect going through it. And here's something I want to explain to you, or at least give you an idea. Let's say air can't get out, okay? It's no different if you blow up a balloon, right? When you blow a balloon up, air is going into that balloon, but that's going to hit the back of that balloon. If we looked at that with a really good pressure transducer, like this Pico, you're going to see air hitting that balloon and wanting to bounce back, right? Boom, 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 right? This is what plugged exhaust looks like sometimes, not all the time, sometimes, okay? Because if I had a valve timing issue, the air is going to be, the airflow through the engine is going to be reduced, but it's not going to hit a wall like this. This thing's hitting, well, it's hitting this restriction and it's bouncing back, right? So think about this. When the intake valve is open, there's exhaust that was still trapped in the cylinder and all that air is pushing back out, right? In my intake manifold, I can see this, right? I can see this. That's pretty interesting. So let's figure this out. Here's number 4's ignition coil. I put my cylinders in 4, 5, 6, 1, 2, 3, 4. I just jam my firing order in, right? And here's my intake pulls. Remember, bank 2's got the negative trim. He's the guy I'm interested in. I look at my intake pulls and look, bank 2's intake pulls. There's 2, 4, and 6. Their intake pulls are lower and they have the ruffles ridges on them. I'm like, no bueno, no bueno, right? So I asked myself a couple questions, right? I said, this has the look of an exhaust path restriction. So the next thing I'm gonna do is I'm gonna jam the transducer in a hole in that bank 2. I'm gonna take one spark plug out, I'm gonna jam that transducer in, because this is gonna triple tell me if I've got some kind of exhaust restriction. I crank this thing over. I got a $1.69. Seems okay, right? What? Look at this. Remember I told you at the top, it should always be the same, right? Would you agree here that I'm not always the same? I go, it's only a couple 3 PSI, but this isn't normal either, right? I told you upper end sealing issues, right? But I also should tell you that if I can't get air out, I could build a little bit more compression too, right? And this is cranking, this isn't running, all right? But that's something that catches my eye. So I fire this thing up, it's idling, right? Seems idle halfway okay. But I just bring my second cursor down and I've got about almost 10 PSI of pressure when the exhaust valve opens, right? Exhaust valve opens here, pressure right there. Look at that. When the engine starts to ramp up, you fire it up. Look at this, 11, 12 PSI. When that exhaust valve opens, there should, at idle or low speed, there should not be that kind of pressure on the exhaust stroke. Think about it. When the exhaust valve is open, my transducer is connected to the exhaust manifold at that point, right? As soon as that exhaust valve opens, my transducer is going to see that, right? Compression gauge ain't going to see that. Ain't no way, right? But my transducer can. This is not good, right? I got pressure here. So I asked myself, it ain't a cam timing problem. This thing can't breathe. Okay. So I fire it up. I do another thing. I do a snap throttle. And right here is when I fire this motor up, and you can see where I snap throttle this. You can see the compression went to 265 PSI. Well, let's blow this up. I'm going to zoom in and I'm going to blow this up. And I'm kind of idling a little higher than normal. I got 25 PSI in the exhaust stroke. I do a snap throttle. I got 52 PSI here in the exhaust stroke. That is way too much. There's 52 pounds of compression building on the exhaust stroke when the exhaust valve is supposed to be open. And it is open, but if it's blocked, it can't breathe. So next thing I'm going to do is I'm going to yank an O2 sensor on that bank. Okay, because that's going to tell me right away. And long story short, this is a Nissan diagram. This thing has a catalytic converter that isn't monitored by an O2, and it has one that is. All right. So we pull the O2 closest to the first cat, right? Right here's that bank 2 cat. The O2 happens to be right here. All right. And we pull that O2 out. This is the post cat O2. And we pull that O2 out and we fire the motor up, right? Already I'm at 0.72 PSI, under a PSI. I do a snap throttle, it's down to 28. That's still a little high, but it's less. So that tells me it's exhaust, right? If it was cam timing, removing an O2 sensor shouldn't have affected that, right? So that's my extra thing I needed, right? So I can tell the guy, hey, we got restricted, exhaust is plugged on this thing, right? But I found it with cranking vacuum, right? Cranking vacuum is what led me to this. So we tore it apart. It turns out this converter here was the one that was junk, okay? This converter here, after the second O2 sensor, was all stopped up in this pipe, and it was actually in this Y right here is where the restriction was. So we replaced this cat, cleaned out all the junk, truck runs perfect, okay? I know it's not really an engine mechanical problem, but I wanted to show you that I can identify a cam timing issue, a bad cam, and a plugged exhaust situation with this. Okay, I got one more case study. I know I'm over time. I'm going to ask Rob and Amanda if they'll let me do this because I'm really close to finishing up, and I hope you guys are still staying tuned. It looks like you are. So let me finish up with this one. This is a good one. All right, this is a friend of mine who comes to our Pico training. He's an excellent technician. He's new at Pico, and he says, "Hey, Chris, he bought the Pico scope. He went through this boat. It's a 7.4 carbureted, right? Old school big block Gen 5 Chevy." He says, "Hey, Chris, this thing, it's got a machine gun backfire. Sounds like the Gaza Strip." And I said, "Hey, listen, I said, he says, I think I've got a valve leakage, right? I think I got a valve leakage. I think I'm going to pull the heads off. He says, but I pressure transducer every single hole and I don't see anything. And he says, I did cranking vacuum and I really didn't see anything. So he asked for my assistance. And I said, sure, Mike, I'm going to go out there. Don't rip these heads off without knowing what you're going after, right? So long story short, the guy buys the boat. Guy gave up diagnosing. The guy owns the boat now, bought the boat, knew it was broke, thought it broke. So first thing they do is they slam dunk a new distributor in. Then they jam a carburetor on. Then they do a raw water pump, fuel pump. This system here, since it's a Gen 5, does not have a fuel pump boss. So Mercury Marine, in their infinite wisdom, they had a raw water pump with a cam lobe in it that ran a mechanical fuel pump. Okay, so he sea trialed the boat 5 times. He's got a bunch of time in it. And I'm not going through all this. You can read it yourself. This is his email to me, everything he did. Okay. And this video I'm not going to play, but this is where it's backfiring through the carburetor. He just puts it wide open, he just gives it a quick snap throttle and it snap, 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 snap through the carburetor. We're going to practice what we preach. We're going to do cranking vacuum, right? So I jam in to the carburetor here, right? There's the 3/8 or some PCV port. We got our transducer in here, all right? And we're going to check cranking vacuum relative compression. We crank this thing over, crank, 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 crank. We ran the carburetor out of gas. So let's blow this up. Cylinder number 1, cranking vacuum, starter motor current. First thing I look at, let's look at the relative compression. Looks pretty good, wouldn't you agree? I mean, all 8 of my, here's 8. This is number, this is 1 through 8. This is another 1 through 8, 1 through 8. I got a pretty big time base here, but there's nothing here. And I've got almost 53 amps of peak to peak current. There's nothing here in relative compression that's going to tell me anything. Looks pretty good. Let's deal with this cranking vacuum. All right. Now I look at this cranking vacuum and the bottoms look pretty good, but I do see an anomaly that repeats, right? There's an anomaly that repeats through this pattern. Repeat, repeat. Would you agree every 8th pole has something going on here, right? We're just cranking here, guys. We ain't running. This is cranking vacuum. Like, oh, right? So let's look at 720 degrees of this, right? I break this out, and right there, that's what attracts me. I look at this like, I don't know. Doesn't look like the rest, right? This is like when you're a little kid and you're at the dentist's office, right? They got those magazines, and which one of these is not like the other one? That's what this diagnosis is. When you start looking at scope patterns and stuff like that, a lot of it is analyzing and comparing, right? I'm looking at this to see, hey, does this look like the rest, right? This is a V8 engine. All these cylinders should be breathing the same. Should be, right? What do I know? We got a mechanical problem. It's mechanical, right? They already jammed a distributor. They jammed a carburetor in. He already put 2 sizes different prop on it because he was 200 RPM short. That's all in there. But we got a mechanical problem here. This mechanical engine, okay? This is why I like cranking vacuum relative compression. I know I sound like a broken record, but this really gives me direction, okay? So I look, I'm like, the top of that pole, now remember what I said, the bottom of that pole is the deepest vacuum. The top of the pole is pressure, right? Or pressure rising in the intake manifold, right? Because you think about it, intake valves are opening and closing. There's going to be pulsations in the intake manifold, right? But something's up here. So guess what I'm doing? I'm going right back to my piston position chart, right? I jam my piston position chart. I pull the firing order. I turn my pistons on. I move the transparency up because I like this dark. And then I'm going to put this in position, right? So I got this in position and I want to focus right here, right? What's going on in that moment in time in this section? That's what I'm interested in. I blow it up a little bit better for your eyes. And first thing I notice is this anomaly seems to begin on number 8's intake stroke. Okay, this anomaly begins on number 8's intake stroke. I'm looking at other stuff here and I'm like, and then it kind of goes right back to normal, right? So, and again, this is not exacto, but this issue kind of begins at number 8's intake stroke. So I gotta ask myself, is this something I should chase, right? That's the question. Is this, Is this something I should change? What could this be? What could be causing, it's not a weak pull, right? It's pulling good vacuum, but the top of this doesn't look like the rest of these so much, you know? So I'm like, huh. So here's what I asked myself, right? All these 8 pulls, right? 1, 2, 3, 4, 5, 6, 7, 8. That one's just a shade deeper. All right. They all pull down, right? It's one of the first things I told you when you began this webinar with me. It's like, hey, you know, I'm looking for even pulls. The pull, you know, the deepest vacuum's at the bottom. So I'm thinking, yeah, looks pretty good to me, right? But whatever's going on, you know, it's starting at that number 8, vacuum pull. So let's rule some things out. Because remember what I said earlier, right? In diagnostics, I love the process of elimination, right? If I can take stuff off my list, I'm a big fan, right? Because there's a lot of things that can do this, right? So I asked myself, I can rule out a leaky intake valve because I don't have any pressure anywhere too much, right? I would actually have more pressure than that. So I know it ain't a leaky intake valve anywhere, right? So intake valves are out of it. Kind of like an exhaust valve. If I had an exhaust valve leak, which I didn't show you today, I would have similar issues, right? I would have a huge rise. This thing is like it started pulling, and it started pulling earlier than it was supposed to, right? I mean, pull goes back, pull goes back, boom, and it's almost like I started pulling vacuum early. You know, it's the first thing I noticed. I don't think I got a leak in any cylinder. All this vacuum pulls down. Remember what I said of cranking vacuum? It tests the cylinder's ability to breathe and to seal. If I had a leak in a piston, in a valve, or something like that, I would not have 8 even pulls. My relative compression starter motor current peaks are great. So I don't believe I've got an issue with a valve sealing issue here. So that only leaves me a couple items, like a valve opening or closing issue, okay? So I've got sealing off my table, okay? That's huge, right? And that's why I say I don't have a leak in any cylinder, right? Ignition or firing order. Let's say I had a carbon track, you know, I'm sure a lot of you guys are good mechanics, right? You could have crank trigger problems, ignition pickup problems. That could cause all kinds of back, right? Crossed wire, right? Maybe you got 5 and 7 cross, 3 and 4, you name it. That could cause some backfiring too, right? Is it ignition system problem or a fuel system problem going to do this? No. This is suck, squeeze, bang, blow. This is old school ignition. This thing ain't breathing right, right? This has got nothing to do with distributor, nothing to do with carburetor, nothing. You see how I can take this and I can kind of make a diagnostic plan based on this, and I can go, it ain't ignition, it ain't valve sealing, it ain't, right? So it's leaving me valve opening, valve closing. That's the only thing that's left, right? This is why this test is so powerful. Okay, so I think about valve overlap, right? I just showed you, you know, a valve overlap issue, right, with a LS-LT L83 engine, right? So I asked myself, hey, Chris, hypothetically, if the exhaust valve closed too early, could that affect that pattern? Yeah, that's what I'm thinking. So let's look at this, right? I've got a valve opening event, right? This is exhaust valve, this is intake. Now, let's pretend the exhaust valve, maybe it's got a cam lobe or something going on. Would you agree that this thing is going to shut a little early? It's going to open late and shut too early. That's why I drew these 2 lines in here, right? So if this thing, if just as a pretend, right, Mr. Rogers' neighborhood, if this line comes down, all right, and my valve kind of closed here, wouldn't that intake maybe have a little bit deeper of a pull, right? Because that exhaust valve closed too early, it could build, because remember, if I go back here, this vacuum is just a shade deeper, and when it would start pulling vacuum maybe a little earlier, right? Because think about it, when that intake valve opens, if there's, you know, with valve overlap, I got just a little bit of exhaust or a little bit of pressure in the cylinder in overlap. If that overlap ain't there, this could happen, right? That's what I tell myself. So that's why I say, hey, Chris, if this exhaust valve closed too early, couldn't that start building vacuum in cylinder 8's intake stroke a little earlier? Yeah, right? Yeah. So I got this shaded gray, same thing, right? If this thing, this shows me valve overlap, right? These things are overlapped, you know, a few degrees, as you know. So I asked myself, Chris, what could do this, right? Worn cam lobe, bent push rod, loose rocker arm, broken rocker arm, you name it. So next step is let's go in cylinder 8, right? 8 could be my guy. So let's take number 8 spark plug out and let's go in. And, oh, excuse me, before I do that, I do one other thing. I actually start this engine up and run it. So I run it with the vacuum transducer in the intake manifold, and I'm revving this thing, right? And I want to do a snap throttle, all right? And I want to see if there's a correlation for this popping through the carburetor, right? So this is number 1, this is number 1, this is number 1, right? I see a spike here, 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 right? Let's blow this up. Let's blow this up, right? I want to blow up this 720 section right here. This is why sometimes cranking, this is why I do cranking vacuum, not running vacuum, but I'm doing this for, I want to show a purpose here. Okay, whatever's going on repeats, right? Repeat, 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 repeat. Something's up, something's up. So let's drop a couple cursors. My lower red horizontal cursor is 0 PSI. That is atmospheric pressure. Would you guys agree that whatever this pulse is here is at 5.67 PSI? Does this have a supercharged 1-cylinder engine? Anybody? Is there a mini blower on cylinder 8 to put 5 PSI? It's got a Whipple charger or something on it? No, right? How could only 1 cylinder have positive pressure in the intake manifold? This is an issue. This is an issue, okay? There's something up here. I don't like it. So let's ID my intake strokes, right? Again, this is a running pattern with a snap throttle. Boom, when it popped back through. This is my pop, right? Pressure in the intake manifold. We know number 1's intake stroke is 360 degrees past the ignition firing event, right? My number 1 firing event is here. This is 360 degrees, right? This is number 1's intake pole. Guess who's next? 8, right? 1843657 This is number 8's intake pole, right? Hey, guess what? When the intake valve opened on cylinder 8, I had pressure. Think about it. The intake valve had to open to create this pressure in the intake manifold, right? I mean, this is why the piston position chart and or doing it the old school way like this is so valuable, because it breaks the events up in my head. And I'm a little slow. I call myself slow Chris sometimes, right? Because I need these visuals to make the correlation, right? I'm taking the clues, right? The clues, the pressure right here. And I'm saying, hey, wait a minute. I looked at this and that pressure pulse happened precisely on number 8's intake stroke. I looked at this 5 or 6 times. I have the same pressure pulse, give or take, 5 PSI. That tells me the intake valve had to open. And the only reason I could have pressure in the intake valve, or excuse me, in the intake manifold when the intake valve opened is the exhaust valve didn't open at the right time, or the exhaust cam is bad, or whatever, okay? That's the only thing that can cause this, okay? That's what I'm thinking. So again, 5 PSI. I use my piston position chart just to drive it home, right? Number 8's intake stroke, right? I've got it highlighted in yellow. It's right here, okay? Kind of like almost right smack dab in the middle, right? Right through the intake manifold. Again, you look at this vacuum pattern, it's very, very hard. I don't recommend anybody look at running vacuum patterns. This is why I like cranking. Cranking it showed up on that top key, remember? Back here. I'll go back here, sorry. Right? This is where it showed up cranking. Running, you can see I don't, this is a lot easier to diag, right? But you do these running patterns, apologize for flipping through here. You do these running patterns, there's a lot more going on, okay? There's a lot more going on. Things are happening way, way quicker. But this I don't like. I don't like it. So I asked myself, Chris, number 8 cylinder is the only intake stroke that's got this spike, right? all testing points in number 8, right? So guess what? Let's go in cylinder. We're taking the transducer. We're going in cylinder only on number 8. I jam number 8. Cranking compression. 142 PSI. Hey, this is a old school big block Chevrolet. That's good compression. 140 PSI. That's okay for this engine, right? So 8.9 to 1, something like that, 9 to 1. That's exactly what I suspect, right? I don't see any tails, or I don't see any rosy thorn bushes or anything down here. Looks okay, right? I fire it up. Kind of looks okay, right? I bring my cursor down. I got 62 PSI. And that 1/3 to 1/2, absolutely. I don't see anything here. I bring my cursors down. Here's my exhaust stroke, right? It's maybe just a PSI above 0. That's kind of shooting my whole exhaust valve theory maybe in the foot a little bit, right? I mean, I was thinking this exhaust valve not opening, but these other ones I showed you before, they kind of had a pressure pulse here, did they not? So something's up here. Something's up here. But we're going to do something. We're going to identify EVO. All right. And you know my numbers, 30 to 60. This is old school General Motors big block, old school stuff. I run this EVO. It's 26 degrees before bottom dead center. Remember my numbers, 30 to 60. Isn't that to the right or late? Isn't that a little retarded, right? I got a loose rocker arm. I got a cam lobe that's wasted, something like that. Isn't that going to be a little later, right? Let's take this another step further. This happens, the engine happens to have, I don't know, this engine was original, but the cams we use, again, not a commercial, we use Melling here for our engines. We have great luck with Melling flat tappet cams in our marine applications, all right? And this is not a flat tappet roller discussion. I know that's a 10 beer discussion. We ain't having that, all right? But what the discussion I do want to have is in Melling's website, this 22-216 cam, which is normal left-hand rotation cam, they tell me, hey, Chris, at 50 thousandths cam lift, your intake valve, it should open at 49, or excuse me, your exhaust valve should open at 49 degrees before bottom dead center. I'm at 26, right? Would you say that's a gross difference? And I just happen to know that's the cam that belongs in this engine. Again, it's a stock engine, but I know for a fact that this is a cam that this engine takes. Again, this isn't a degree wheel. I'm not exacto, but I'm in the neighborhood. But I'm 20-some degrees. I'm quite a bit degrees off. Right? I'm not no onesie twosie here. I'm a mile off. So I'm at 26. Right? That thing's way late. I do a light throttle snap. Thing's sitting there. I got the transducer in there, and I do a light throttle snap. This closes the deal. Look at this. I see these extra pressure pulses, right? The big ones are TDC. The second ones, that's my exhaust stroke. Look at this. I do a snap throttle. This thing is trapping the highest I saw right here, 50, almost 60 PSI, right? Would you agree a worn cam lobe or something that is suspected here? I can't get exhaust out. Now this one, we had to snap it to see it. I showed you other ones that you could see it without, like that LS motor and all that stuff. This one I had to do a little snap, but the clues were still there. We could still get there. We could still get there, right? I do a wide open throttle snap at the dock, right? Look at this, 100 PSI. Is your Sears and Rubbish or Harbor Freight or whatever your favorite brand compression gauge going to tell me that? No way. This is why I don't use compression gauges anymore. I know I'm a broken record, but ever since I've learned how to do this, you see why the diagnostic benefit of this is unbelievable. And we didn't take a valve cover off. We didn't do any of that. We took one spark plug off and went in through the PCV port, right? I blow this up again, right? Look at this, 100 PSI, horrible, as they say. Horrible, horrible, horrible. Now, on a big snap throttle, you probably will see 15 to 30 PSI on most engines, all right? Because you're trying to move a lot of air, okay? But 100, this thing's got 142 PSI of cranking compression. Why do you think this thing sounds like a machine gun through the intake or through the intake manifold, right? That exhaust can't get out. Intake valve opens, poof, right back up where it came from. Send it back, right? Give it back to the earth, right? Get it out of here. But the cranking vacuum showed it. The cranking vacuum showed it, right? Now I put EVO in here. It's actually supposed to be a little bit later when you rev it up like that. But you can see that my exhaust valve never really opened, right? When I was really revving this thing up, when I really needed to move that air, it couldn't happen. So I tell them all the testing points to an exhaust valve, a number 8 cylinder that doesn't open too late, or opens too late and closes too early. I tell my friend Mike, I said, Mike, just for the rest of the case study, let's pull the valve cover off and look. I will play this video. You don't need the sound, all right? And we got the valve cover off just on the right bank, okay? And that's obviously the exhaust valve on cylinder 8. I'm gonna wasted, right? That's right. Guess what? It's shrunk. We got it. But I didn't need to do that, right? This guy checked compression. He did all that, right? They started messing around with distributors, everything else. But this is a mechanical problem, right? Again, as a repeat, a cranking or traditional compression test would never find this. You would never find it, right? You would have to pull valve covers off. I know a lot of your race motor stuff, the valve covers come off in 10 seconds. But some of you guys, I'm sure on here, you work on boats, you're a production builder, you're sending engines out to people, right? Taking a valve cover off could be a 4 or 5 hour chore, right? Who wants to take a valve cover off a 674 diesel? Not me, right? I don't want to take a valve cover off of anything, okay? But the cranking vacuum showed the anomaly. That's the key. That led me to look at number 8. You know, the question is, Chris, what were the clues, right? Again, this is a crime scene, right? I'm using the clues to figure out what to go after, right? I see that cranking, I see that vacuum anomaly, just number 8, that automatically tells me, Chris, let's jam that transducer in there. Let's see what the heck's going on. Guys, 25 minutes. I ain't bragging, okay? But you tell me how else you can do that. There's no way. You know, this scoping gives me X-ray vision, man. I feel like Superman. You can go in and go, and you can pin down these mechanical engine problems. And this is just the tip of the iceberg of this tool. I mean, this tool is absolutely phenomenal. I mean, the class I do on this, it's 4 days. We spend day 1 with engine mechanical, day 2 is ignition, day 3 is fuel systems, day 4 is scan tool interpretation, and how to use the scope to find boats that cut out, miss, backfire, and all kinds of stuff when you've got crank trigger problems and stuff like that. But you know what this Marine did? He goes, you know what? We ain't messing with this. We got all that metal in there. We ordered a long block. So they put a long block in this thing from whoever they get their engines from. They put it in. The guy boated all season. Didn't have one issue. So with that, my presentation is basically done. You can reach out to me if you got any questions, comments about this presentation or anything else I've done. You're more than welcome to reach out to me via email. I do have our own YouTube channel. I haven't updated it much lately. I've been too busy training and teaching and working here at our shop. I'm our only machinist in this shop, so when I'm not here, nothing gets done in the machine shop. If you're interested and want to do some hands-on with this, I'm pretty much done with this for the year. I just finished up my last 4-day class a couple weeks ago, but I work part-time for eHobie Career Center, and it's a Marine lab, and we take 18 students at a time, and I show you the nuts and bolts of this equipment. We've got over 15 engines in that lab. We got outboards, old school Chevy. Even if you're a car guy, if you want to learn how to do this, it's kind of nice on a Marine engine on a stand, right? Because you can get just like these guys right here. You can get right there, okay? So, you know, when that engine's in the chassis or in the boat, you know, you're on your knees and everything. That kind of sucks. But like I say, if you're interested, you're more than welcome to hit us up on that. And again, I've got a Facebook page, our company. You can follow that for information. I got some case studies on YouTube and that, and that's pretty much it. So I hope you guys liked it. If you've got any questions, I can stick around and answer them.
Well, Chris, I mean, great job. There's a lot going on there that you've covered, and you know, there's, you know, I think this opened up a lot of eyes for folks. I mean, it really did. I'm no different than you. You know, nobody likes to get dirty. Nobody likes to get, you know, knuckles that are bleeding and that kind of stuff. So to use these methods to diagnose some of this stuff, you have literally opened our eyes a whole bunch for sure.
That's why I try to keep my hands like the dishwasher at a restaurant, right? You know, I mean, you want to keep them clean. I don't want to get dirty. Hey, the older I get, the less I want to screw around and pull stuff apart, right? I mean, who wants to take something apart? That's so much work.
so so true. So we do have a few questions that have come in, and if some of these questions are something that maybe you need to reach out directly to the person that's asked, by all means, I'll share the information. But we've got one here, and they've asked, I would also like to know how to use exhaust pressures for engine diagnosis with the Pico and transducer. Can exhaust tell us anything more than intake vacuum and relative compression?
The answer is yes. I don't do tailpipe testing because half the time I'm working on a boat, I can't get the tailpipe. Obviously, in our repair shop, we have a 10-bay repair facility with 4 technicians, but I haven't really perfected the exhaust tailpipe stuff. There is an algorithm where you actually put that transducer or a first look device in the tailpipe and you trigger off a cylinder, because what you're looking for there is, like, remember the old dollar bill test, like, Rob, when you take a dollar bill and go to a tailpipe and it would do that.
Right?
Well,
Yep.
if I go back, if you don't mind, I just want to explain something, because this is actually a very good question. You know, here where this vacuum pocket, Rob, okay? So right here is 0 PSI. That's the vacuum pocket. Well, think about this. When you have a misfire in a cylinder, okay, and by the way, the definition of a misfire is incomplete combustion. Could be water in the cylinder, could be no spark, no fuel, whatever, oil fouled, I don't care, you name it. But what happens is normally, remember, the piston is getting drugged down the cylinder here because my transducer's in here. Normally there would be combustion pressure here. So there's not going to be a vacuum pocket. This is why your dollar bill sucks in your tailpipe, assuming you got a tight exhaust, right? I'm sure you've seen videos of old school mechanics, right, where they take a dollar bill and your dollar bill just sucks back up to the tailpipe. You know what I'm talking about? That dollar bill test is, you're seeing this expansion pocket of the vacuum, right? Normally, I would not have vacuum here if combustion took place. Does that make sense? So
It does. Yep.
So what that tailpipe test does on misfires and stuff like that is, I believe, and I could be wrong, and if I am wrong, some of you, you're welcome to correct me, is you're looking at that pocket there in the exhaust and you're tracing that back to a cylinder. But I personally have not perfected exhaust tailpipe pressure transducer diagnostics. I haven't perfected anything, you know, but I use this quite a bit. And I normally can get to it. And like I say, when I'm working on a boat or an outboard, I can't get to the tailpipe anyway. So I haven't spent a lot of time on it, to be honest with you.
Another question is, how are you checking vacuum pull on a diesel? How do you check valves?
Good question. You can't, because on a diesel, you don't hold vacuum, right? Now, if you wanted to get cute and it's a modern diesel and you've got a scan tool, you could probably close the EGR flapper like on a 6.4 or 6.7. Yeah, I cannot use the vacuum on the diesel. But what you could do, which I haven't done yet, is you could take, like, let's just say you got a coffee can. Let's say you got a Folgers plastic coffee can, and you create your own orifice. So take like a 1-inch hole saw or something and drill a 1-inch hole in there, and then put that over the intake of the diesel engine, and then connect your transducer to that. You could probably see vacuum pulls here. Because the issue on a diesel is I've got nothing to hold vacuum. That's why diesel engines don't have vacuum. There's nothing to hold it, right? You know, there's no throttle blade. The only reason you have a throttle blade on a modern diesel is to promote and to promote EGR flow at low speeds, right? So when you're running down a road, we close that blade so we can get EGR to flow in the intake manifold. And as an oh shit, we can close it on a runaway if it's programmed to. But you could create, because I've ran into some engines that when you crank the engine over, the throttle blade opens, specifically Volvo Penta. A Volvo Penta LS engine and a Volvo Penta 5.7 GXI with an EGC controller, they do that. They do that, and the throttle blade is open, and you can't get vacuum. The only reason I get those vacuum pulls is I'm pulling against a restriction, which in a gas engine is the throttle blade.
Okay, well, super. Chris, if there's any questions that come in after the fact, I know we'll respect everybody's time and let them get back to work. And same with you. I'm sure you're not making money and talking to me, right? That's for sure. So we'll.
Yeah, that's okay. Stock market. I'm doing all right. No, I'm just.
But
well,
yeah,
looks like everybody stayed around, so that's pretty good. I apologize. I went overtime. I had a lot to cover, and I did pack it in there a little bit, but I want to give guys the idea. All I want to do is just turn on a light bulb here, right? My goal was to say, hey, look, this is just some of the things you can do with this equipment and some practice, and I can't overemphasize the practice. You've got to practice. You ain't gonna be down one out of the gate. You ain't going to come in here with this tool and you ain't going to start knocking all this stuff out of the gate. It is, like I said, it's like wine, right? It's acquired taste.
Well, Chris, thank you again. Yeah, very much appreciated. And like I say, if anybody's got any questions at all, Chris would be more than happy to answer them. He's a really great contact for us in both the marine world and the diagnostic world, so he can help us out with any questions you've got.
Thank you, guys. Thanks for having me, and thanks to everybody out there for listening. I appreciate your time and your interest in what we have to do here at the AERA and this specific webinar and all our webinars, to be honest with you. So thanks to everybody else, and for sure.
Thank you, everyone, for your time. We know time is precious during the day, and we appreciate you taking time out to watch these webinars. When you leave today, there will be a survey that pops up. Take a moment, fill that out, let us know how we're doing, if there's anything you'd like to see, and there's also a spot in there to ask any questions you may have for Chris, as well as any questions you may have for us. And then real quick, lastly, if you need to get a hold of anyone at AERA, you can call us at 815-526-7600, or as Rob mentioned, feel free to shoot either of us an email. My email is amanda@aera.org, or there's rob at aera.org, and we'll be happy to answer your questions or get you in touch with the right person to get those taken care of. So with that, we will let you go, and we hope you have a great rest of your day.